Imagine a magnet so powerful that it could erase every credit card on Earth from halfway to the moon. A magnet so strong it would pull the iron from your blood if you got too close. A magnet capable of warping the very atoms that make up matter itself. This isn't science fiction. These objects exist. They're called magnetars, and they are the most magnetic objects we've ever discovered in the universe. A magnetar is a type of neutron star, the collapsed core of a massive star that exploded in a supernova. But while a typical neutron star might have a magnetic field 1 trillion times stronger than Earth's, a magnetar takes this to an almost incomprehensible extreme. Its magnetic field is 1,000 times stronger still, 1 quadrillion times more powerful than the magnets holding notes to your refrigerator. To put this in perspective, if a magnetar existed at the distance of the moon from Earth, it would strip the magnetic data from every credit card, hard drive, and electronic device on the planet instantly. At a distance of 1,000 kilometers, about 600 miles, the magnetic field would begin disrupting the molecular bonds in your body. Your atoms would literally start to reshape themselves along the magnetic field lines. And this is from an object only about 20 kilometers across, roughly the size of a city, spinning in many cases several times per second, generating more energy in a single explosive burst than our sun produces in decades. Magnetars are among the most extreme objects in the cosmos, places where the normal rules of physics are pushed to their absolute breaking point. They challenge our understanding of matter, energy, magnetism, and the fundamental forces that govern reality. Tonight, we're going to explore these cosmic monsters in detail. We'll discover how they form, why they're so impossibly magnetic, what happens when they erupt, and what they can teach us about the universe's most extreme environments. We'll learn about starquakes that release more energy than the sun produces in a year, about magnetic fields so intense they create exotic particles out of empty space, about observations that changed our understanding of stellar death and cosmic violence. But we'll take our time. We'll build our understanding piece by piece, connecting the familiar to the extraordinary, the everyday to the extreme. By the end, you'll understand not just what magnetars are, but why they exist, how we discovered them, and what makes them some of the most fascinating objects in all of astronomy. So settle in, let the day's concerns drift away. We're about to journey to some of the strangest places in the universe. Objects so extreme they seem impossible, yet so real we can observe them from Earth, billions of light years away. Let's begin with the basics. What exactly is a neutron star, and how does one become a magnetar? Before we can understand magnetars, we need to understand neutron stars. And to understand neutron stars, we need to understand what happens when massive stars die. Stars spend most of their lives in a delicate balance. Gravity pulls inward, trying to collapse the star. Nuclear fusion in the core pushes outward, counteracting gravity with radiation pressure and heat. For millions or billions of years, these forces balance perfectly, and the star shines steadily. But fusion requires fuel, and eventually, even the largest stars run out. For stars much more massive than our sun, at least 8 times more massive, and sometimes dozens of times larger, the end comes dramatically. When the core runs out of elements to fuse, the outward pressure suddenly disappears, and gravity wins. The core collapses, not slowly, but catastrophically. In less than a second, a sphere of iron and other heavy elements the size of Earth compresses down to a ball, roughly 20 kilometers across. That's about 12 miles in diameter, the size of Manhattan or Greater London. A sphere you could fit inside a typical city. But this sphere contains more mass than the sun. Imagine crushing our entire sun, which has a diameter of about 1.4 million kilometers, down to the size of a city. The density is almost beyond comprehension. The collapse is so violent, so sudden, that it rebounds. The outer layers of the star, which were falling inward at a significant fraction of light speed, suddenly slam into the compressed core and bounce back outward. This creates a shockwave that tears through the star, heating it to billions of degrees and triggering a supernova, one of the most energetic explosions in the universe. The outer layers are blasted into space, creating the spectacular nebulae we observe with telescopes. But the core remains. compressed, unimaginably dense, spinning rapidly from conservation of angular momentum. This is a neutron star. Let's understand just how dense these objects are. In a normal atom, most of the space is empty. The nucleus is tiny, about 100,000 times smaller than the atom itself. Electrons orbit in clouds far from the nucleus. If an atom were the size of a football stadium, the nucleus would be smaller than a marble at the center. But in a neutron star, that empty space is gone. The electrons have been forced into the protons, creating neutrons through a process called electron capture. The neutrons pack together as tightly as physically possible, actually touching each other, like marbles packed in a jar with no space between them. This is called neutron degeneracy. It's a quantum mechanical effect where neutrons resist being compressed into the same quantum state. This resistance degeneracy pressure is what holds the neutron star up against gravity. It's not heat or nuclear fusion anymore. It's a purely quantum phenomenon. The result is matter with a density of about 400 million tons per teaspoon. That's roughly the mass of all humanity. Every human being alive today compressed into a volume smaller than a sugar cube. If you could somehow scoop up a teaspoon of neutron star material and bring it to Earth, it would weigh as much as Mount Everest. It would instantly fall through the ground, through the Earth's crust, plunging toward the planet's core under its own immense gravity. Neutron stars are also incredibly small for their mass. Despite containing 1 to 2 times the mass of our Sun, they're only about 20 kilometers in diameter. This creates an intense gravitational field at the surface, about 2 billion times stronger than Earth's gravity. On a neutron star's surface, you would weigh billions of times more than you do on Earth. A single step would require more energy than launching a spacecraft. Your body would be instantly flattened to a layer about the thickness of an atom. The gravitational pull would be so intense that light itself is bent significantly, allowing you to see around the curve of the star's surface. Neutron stars also spin rapidly because of conservation of angular momentum. When the star's core collapses from a sphere, millions of kilometers across to one only 20 kilometers across, its rotation speed increases dramatically, like an ice skater pulling in their arms to spin faster. Many neutron stars rotate several times per second. Some spin hundreds of times per second. The fastest known neutron star rotates 716 times per second. That's 43,000 revolutions per minute. The surface at the equator is moving at about 15% the speed of light. And this is where things get interesting for our story. Because rotating neutron stars also have magnetic fields, and those magnetic fields can be extraordinarily strong. A typical neutron star might have a magnetic field strength of about 1 trillion Gauss. For context, Earth's magnetic field at the surface is about half a Gauss. A strong refrigerator magnet is about 100 Gauss. The most powerful continuous magnetic field ever created in a laboratory is about 100,000 Gauss. A neutron star's field is 10 million times stronger than the strongest laboratory magnets. This is already extreme. But magnetars go further still. A magnetar's magnetic field reaches up to 100 quadrillion Gauss. That's 100 quadrillion Gauss. Written in scientific notation, it's 10 circumflex, 15 Gauss. Or, in the units physicists prefer, about 10 circumflex, 11 Tesla. This is 1,000 times stronger than a typical neutron star. 10 billion times stronger than the strongest lab magnets. 20 quadrillion times stronger than Earth's field. At this strength, the magnetic field itself becomes a source of energy and exotic physics. It can create particles out of empty space. It can warp atoms into elongated shapes. It can generate X-rays and gamma rays powerful enough to affect Earth's atmosphere from thousands of light years away. But how does a neutron star develop such an impossibly strong magnetic field? Why are some neutron stars normal and others become magnetars? To answer that, we need to look more carefully at what happens during the supernova and the birth of the neutron star itself. When the core collapses, it doesn't just compress, it also heats up dramatically. The temperature reaches billions of degrees. At these temperatures, matter exists in exotic states, quark-gluon plasma, neutron-rich nuclear matter, possibly even stranger forms we don't fully understand. The collapse also generates powerful convective currents, churning motions in the incredibly hot, dense matter. These convective currents, combined with the star's rapid rotation, can generate magnetic fields through a process called a dynamo. This is similar to how Earth's magnetic field is generated by churning molten iron in our planet's outer core. But in a neutron star, the conditions are far more extreme. The matter is incomparably denser, the rotation is far faster, and the initial magnetic field that gets amplified can already be quite strong, inherited from the magnetic field of the original massive star. In most cases, this dynamo process generates the trillion gas fields typical of regular neutron stars, but in rare cases, perhaps once in every 10 neutron stars, though we're not entirely sure of the ratio, something different happens. The dynamo runs away. The magnetic field amplifies to incredible strength in just a few seconds during and immediately after the collapse. The exact mechanism is still debated, but it likely involves the perfect combination of rapid rotation, strong convective flows, and perhaps the details of how the supernova explosion unfolds. The result is a magnetar, a neutron star with a magnetic field so strong it dominates the object's behavior and evolution in ways unlike any other star. These magnetic fields are not static, they're dynamic, evolving, and incredibly violent. They twist through the star's crust, they create enormous stresses, and periodically they release that stress in explosive bursts that can be detected across the galaxy. But we're getting ahead of ourselves. To truly appreciate what makes magnetars special, we need to understand what such extreme magnetic fields actually do. How do they change physics? What happens to matter in these conditions? And what makes them observable from Earth? Let's explore the physics of extreme magnetism. Magnetic fields are something we experience every day. They hold notes to refrigerators, orient compass needles, and keep electric motors spinning. They're invisible, yet tangible in their effects. But in our everyday experience, magnetic fields are weak. To understand magnetars, we need to understand what happens when magnetic fields become strong. Not just strong, but incomprehensibly powerful. And at these extremes, magnetic fields stop being gentle guiding forces and become dominant, violent, reality-warping phenomena. Let's start with a simple question. What is a magnetic field? At the most fundamental level, a magnetic field is a region of space where charged particles experience a force perpendicular to their motion. It's one aspect of the electromagnetic force, one of the four fundamental forces of nature, alongside gravity, the strong nuclear force, and the weak nuclear force. Magnetic fields are created by moving electric charges. Currents in wires create magnetic fields. Electrons orbiting atomic nuclei create magnetic fields. And in neutron stars, churning charged particles in the interior create magnetic fields. These fields have direction and strength. We measure strength in units called Gauss or Tesla. 1 Tesla equals 10,000 Gauss. Earth's field is about 0.5 Gauss. A strong bar magnet might be 100 Gauss. An MRI machine operates at about 10,000 to 30,000 Gauss. Now, let's scale up to neutron star territory. A typical neutron star has a surface magnetic field of about 1 trillion Gauss, 10 circumflex, 12 Gauss. At this strength, interesting things start to happen. Charged particles spiraling along magnetic field lines emit synchrotron radiation, high-energy light produced by their acceleration. This is how we detect many neutron stars. They emit beams of radio waves and X-rays that sweep past Earth like lighthouse beams as the star rotates. But even at 1 trillion Gauss, atoms remain atoms. Electrons still orbit nuclei. Molecules can still form. The chemistry might be different, but the fundamental structure of matter is unchanged. Now jump to magnetar territory. 100 quadrillion Gauss, 10 circumflex, 15 Gauss. Here, everything changes. At this strength, the magnetic field energy density, The energy stored in the magnetic field per unit volume exceeds the mass energy density of matter itself. Let that sink in. The magnetic field contains more energy than the mass of the matter it's permeating, according to EMC Quadrate. This means the magnetic field isn't just influencing matter, it's dominating it, controlling it, reshaping it. Let's explore what this means for atoms. In a normal atom, electrons orbit the nucleus in roughly spherical clouds determined by quantum mechanics. These orbitals are stable and define the chemistry of each element. But in a strong magnetic field, electrons experience an additional force. Their orbits become compressed perpendicular to the field and elongated along it. Instead of spherical orbitals, you get cigar-shaped ones. At the field strengths found on magnetars, this distortion is extreme. Atoms are squeezed into thin, elongated shapes hundreds of times longer than they are wide. A hydrogen atom, normally about 0.1 nanometers across, becomes stretched into a shape a few nanometers long, but only 0.001 nanometers wide. This changes chemistry completely. Atoms can no longer bond in normal ways. Molecules as we know them cannot form. Instead, you get chains of atoms aligned along magnetic field lines, creating exotic forms of matter that exist nowhere else in the universe. Iron atoms, which would normally form metallic crystals, instead form strange chain-like structures. The surface of a magnetar isn't like any solid we know. It's a bizarre lattice of atomic chains aligned with the magnetic field, creating a substance with properties unlike any material on Earth. But the effects go deeper still. Magnetic fields at magnetar strength affect fundamental particles and even empty space itself. In quantum field theory, what we think of as empty vacuum isn't truly empty. It's filled with fluctuating quantum fields, virtual particles constantly appearing and disappearing in matter-antimatter pairs. Normally, these fluctuations are symmetric in all directions. But a strong magnetic field breaks this symmetry. It aligns these quantum fluctuations, creating an effect called vacuum birefringence. Space itself becomes optically birefringent, meaning light polarization changes as it travels through the magnetized vacuum. This was a theoretical prediction for decades, only recently confirmed by observing light from magnetars. The vacuum around a magnetar acts like a crystal, with different optical properties in different directions, purely because of the magnetic field's influence on quantum fluctuations. Even more exotic, at magnetar field strengths, the quantum vacuum can spontaneously create electron-positron pairs. The magnetic field contains so much energy that it can directly convert that energy into matter and antimatter, pulling particles into existence from apparently empty space. This process, called magnetic pair creation, happens naturally around magnetars. The space surrounding these objects is filled with electrons and positrons being created from vacuum fluctuations, then accelerated to near light speed by the magnetic field, radiating high-energy photons before annihilating back into energy. It's a seething, dynamic environment where the boundary between energy and matter blurs, all driven by the magnetic field's incredible strength. The magnetic field also affects neutrons and other particles. In the extreme fields at a magnetar's surface, neutrons, which have no electric charge and normally don't interact with magnetic fields, develop an induced magnetic moment that causes them to align with the field. This affects the neutron star's crust structure. The solid crust, made of neutron-rich nuclei in a lattice, becomes an isotropic, meaning its physical properties vary with direction. It's stiffer in the direction parallel to the magnetic field and weaker perpendicular to it. This anisotropy creates enormous internal stresses. The crust is being pushed and pulled by magnetic forces that rival and sometimes exceed the gravitational forces holding the star together. It's like a rigid shell with enormous tension built into it, stressed to near the breaking point. And periodically, it does break. The crust fractures in what's called a starquake, a sudden release of accumulated stress, similar to an earthquake, but involving the entire neutron star crust. These starquakes are among the most violent seismic events in the universe. When a starquake happens, the crust shifts suddenly. This shift disturbs the magnetic field threading through it. And because the magnetic field is so strong, this disturbance releases an enormous amount of energy that was stored in the twisted, stressed magnetic field lines. The result is a burst of high-energy radiation, X-rays and gamma rays, that explodes from the magnetar's surface. These bursts can release more energy in 1/10 of a second than the sun emits in an entire year. And we can detect them from Earth, even when they occur thousands of light years away. But there's another, even more dramatic phenomenon that magnetars produce: giant flares. These are the most powerful magnetic eruptions in the universe, and they're so energetic they affect our own planet's atmosphere when they occur in our cosmic neighborhood. To understand giant flares, we need to understand magnetic reconnection, a process that happens throughout the universe wherever magnetic fields exist, but which reaches its ultimate extreme on magnetars. Magnetic field lines are conceptual lines showing the direction and strength of a magnetic field. In a stable configuration, these lines are smooth and don't cross each other, but when field lines of opposite direction are brought together, they can suddenly reconnect, snapping into a new configuration and releasing the energy that was stored in the field's geometry. On Earth, magnetic reconnection powers auroras and solar flares. On the Sun, it causes coronal mass ejections. But on a magnetar, magnetic reconnection releases energy on an unimaginable scale. A magnetar's magnetic field is incredibly twisted and stressed. Field lines are wound up by the star's rotation and by motions in the interior. Over time, this winding stores enormous energy, like winding up a spring or twisting a rubber band. Eventually, the field becomes unstable. Field lines of opposite polarity are brought close together, and suddenly they reconnect. Huge loops of magnetic fields snap and reconfigure in a fraction of a second. The energy release is staggering. In the most powerful giant flare ever observed, which occurred on a magnetar called SGR 1806-20 in December 2004, the burst released about 10 circumflex 46 ergs of energy in 1/10 of a second. To put this in perspective, that's more energy than the sun produces in 150,000 years, released in a fraction of a second. It's equivalent to converting about twice the mass of Earth's moon directly into energy, from an object the size of a city. The gamma rays from this flare traveled 50,000 light-years across space. When they hit Earth, they ionized the upper atmosphere, disrupting radio communications even though the event lasted only milliseconds. Satellites were temporarily blinded by the intense radiation. This happened from an object halfway across the galaxy. If a similar flare had occurred on a magnetar just 10 light-years away, close by galactic standards, it could have damaged Earth's ozone layer, potentially causing an extinction event. Fortunately, we know of no magnetars that close to us. The nearest confirmed magnetar is about 9,000 light-years away, far enough to be safe, but close enough for detailed observations. These magnetic phenomena, the warping of atoms, the creation of particles from vacuum, the starquakes, the giant flares, all emerge from the same source, a magnetic field so strong it rivals gravity in its influence over matter and energy. But this raises an important question. How can such a strong magnetic field be maintained? Why doesn't it dissipate? And what powers these incredible eruptions? The answer lies in the magnetar's interior, where the magnetic field is anchored, and where the energy ultimately comes from. To understand this, we need to look inside the neutron star itself. The interior of a neutron star is divided into layers, each with different properties. At the surface is a thin atmosphere, just centimeters thick, made of iron atoms or exotic particles. Below that is the crust, about a kilometer thick, made of neutron-rich nuclei in a crystal lattice, with free electrons moving between them. Deeper still is the outer core, where nuclei merge into a neutron fluid with a small fraction of protons and electrons. And at the center is the inner core, where matter may exist in forms we don't fully understand, possibly including quark matter or other exotic states. The magnetic field threads through all these layers, but it's anchored primarily in the crust and outer core. The field lines are, in a sense, frozen into the conducting material, a phenomenon called flux freezing. This means the field lines move with the matter, and the matter moves with the field lines. If the crust shifts in a starquake, the magnetic field shifts with it. If the magnetic field twists due to motions in the core, the crust feels the stress. This coupling between the magnetic field and the matter is what makes magnetars so dynamic and so violent. Energy can be stored in the magnetic field through twisting and stressing, then suddenly released when the stress becomes too great. The ultimate energy source is the magnetar's rotation. As the star spins, any slight misalignment between the magnetic axis and the rotation axis causes the magnetic field to exert a torque on the star. This torque acts like a brake, gradually slowing the rotation. The rotational energy, which is enormous for a rapidly spinning neutron star, is converted into magnetic energy. This process, called magnetic braking, powers the magnetar's emission and provides the energy for the eruptions. Over time, the magnetar spins down, losing rotational energy. The magnetic field also decays slowly as currents in the interior dissipate. On timescales of thousands to tens of thousands of years, a magnetar gradually fades, becoming a more ordinary neutron star. But during its active phase, a magnetar is among the most violent and energetic objects in the cosmos. And understanding them has revolutionized our knowledge of neutron stars, stellar evolution, and extreme physics. Let's turn now to how we discovered these remarkable objects and how we observe them from Earth. We've explored how magnetic fields affect matter and space itself. But the magnetic field doesn't end at the star's surface. It extends outward, creating an invisible structure called the magnetosphere, a vast, dynamic region where the magnetic field dominates over all other forces. Understanding the magnetosphere is crucial to understanding magnetars, because this is where much of the action happens. The bursts we observe, the X-rays we detect, the particles that stream away into space, all of these phenomena occur in or are shaped by the magnetosphere. Let's start with a basic question. What exactly is a magnetosphere? A magnetosphere is a region of space surrounding a magnetic object where the magnetic field is strong enough to control the motion of charged particles. Earth has a magnetosphere shaped by our planet's magnetic field as it interacts with the solar wind. Jupiter has an enormous magnetosphere extending millions of kilometers into space. But a magnetar's magnetosphere is something else entirely. The magnetosphere of a magnetar extends roughly 1,000 kilometers from the star's surface, about 50 times the star's radius. This might sound modest compared to planetary magnetospheres, but remember that a magnetar is only 20 kilometers across. The magnetosphere is a significant extension of the star's sphere of influence. Within this region, magnetic field lines emerge from one magnetic pole, arc through space, and return to the other pole. These field lines are invisible, but they have real physical effects. Charged particles, electrons, positrons, ions, are trapped on these field lines, spiraling along them and unable to move perpendicular to them. The result is a structured environment with distinct regions, each with different properties. Near the stellar surface is the closed field line region. These are magnetic field lines that begin and end on the star's surface, forming loops. Particles trapped on closed field lines are confined near the star, bouncing back and forth between the two magnetic poles. They can't escape. This is similar to Earth's Van Allen radiation belts, where particles trapped on magnetic field lines create zones of intense radiation around the planet. But on a magnetar, the trapped particles are far more energetic, and the field far stronger. Farther out, the field lines open. These are magnetic field lines that extend to great distances, potentially connecting to the interstellar magnetic field. Particles on open field lines can stream away from the star, creating a particle wind similar to the solar wind, but far more intense. The boundary between closed and open field lines is called the last closed field line. The distance to this boundary depends on the field strength and geometry, but for a magnetar, it's typically a few hundred kilometers from the surface. Beyond this boundary, the magnetic field still exists, but is less confining. Particles can escape more easily, and the magnetosphere begins to interact with the surrounding environment. The supernova remnant, the interstellar medium, or any nearby companion star. But here's where things get interesting. The magnetosphere isn't static. It's constantly changing, twisted by the star's rotation, disturbed by eruptions from the surface, and stressed by the evolution of the magnetic field itself. As the magnetar rotates, its magnetic field rotates with it. At large distances, the field lines would have to move faster than light to keep up with the rotation. This is impossible, so instead, the field lines break and reconnect, creating a boundary called the light cylinder. The light cylinder radius is the distance where the rotation speed would equal the speed of light. For a magnetar rotating every 5 seconds, the light cylinder is about 240,000 kilometers from the center, about 12,000 times the star's radius. Inside the light cylinder, the field co-rotates with the star, dragging particles along. Outside the light cylinder, the field cannot maintain co-rotation, and a complex structure of currents and waves develops. This is where the magnetar's rotational energy is converted into electromagnetic radiation and particle energy. The region between the stellar surface and the light cylinder is called the magnetosphere proper. It's here that most of the high-energy phenomena we observe originate. Now let's consider what's in this magnetosphere. It's not empty. It's filled with a plasma, a hot gas of charged particles consisting of electrons, positrons, and ions. Where do these particles come from? Some are pulled from the stellar surface. At the magnetic poles, the intense magnetic field can yank atoms from the solid crust, ionizing them and accelerating them outward along field lines. This process, called field-aligned acceleration, creates streams of particles flowing from the poles. But most particles are created within the magnetosphere itself through a process called pair creation. Remember that the magnetic field is so strong, it can create electron-positron pairs from vacuum fluctuations. But there's another, more efficient mechanism operating in the magnetosphere. High-energy photons, gamma rays, traveling through the intense magnetic field, can spontaneously split into an electron and a positron. This is called magnetic pair production. It's only possible when the photon energy and the magnetic field strength satisfy certain conditions. But in a magnetar magnetosphere, these conditions are easily met. Here's how it works. A gamma-ray photon from the stellar surface travels outward through the magnetosphere. As it moves through the intense magnetic field, the quantum vacuum becomes polarized. At a certain point, the photon's energy and the field strength combine to make pair creation energetically favorable. The photon disappears, and in its place are an electron and a positron, each carrying roughly half the photon's energy. These particles are immediately accelerated by the magnetic field, spiraling along field lines. As they accelerate, they emit more gamma rays through synchrotron radiation. These new gamma rays can themselves undergo pair production, creating more particles, which create more gamma rays, which create more pairs. This is called a pair cascade, or electromagnetic cascade. The result is that the magnetosphere becomes filled with a dense plasma of electrons and positrons, all moving at relativistic speeds, all radiating high-energy photons. This plasma is sometimes called a pair plasma, or an electron-positron plasma. The density of this plasma is enormous, up to 10 circumflex, 14 particles per cubic centimeter near the stellar surface, though it decreases with distance. For comparison, Earth's atmosphere at sea level has about 10 circumflex, 19 molecules per cubic centimeter, so the magnetar's magnetospheric plasma is tenuous by terrestrial standards, but incredibly dense for an astrophysical environment. This plasma screens the electric field. In ordinary circumstances, a rotating magnetic object generates an electric field due to the motion of the field lines. But in a dense plasma, free charges rearrange themselves to cancel this electric field almost completely. This is called electric field screening. However, the screening isn't perfect. Small electric field components remain, and these can accelerate particles to extreme energies. Additionally, in regions where the plasma density is low, stronger electric fields can develop. These accelerating regions are crucial for understanding magnetar emission. When particles are accelerated to high energies, they radiate copiously. This radiation is what we observe as the magnetars X-ray and gamma-ray emission. Let's trace the path of a single electron in the magnetosphere to understand this better. Imagine an electron is created by pair production at an altitude of 50 kilometers above the stellar surface. It's born with an energy of about 10 million electron volts, 10 MeV, about 20 times the rest mass energy of an electron. The electron immediately feels the magnetic field. It begins to spiral along a field line, moving toward one of the magnetic poles. As it spirals, it experiences a force perpendicular to its motion due to the curved field line. This is called curvature radiation. Curvature radiation is emitted whenever a charged particle moves along a curved path at relativistic speed. It's similar to synchrotron radiation, but arises specifically from following the curvature of magnetic field lines. Our electron emits curvature radiation in the form of high-energy photons, X-rays and gamma rays. These photons carry away energy, so the electron slows down slightly. But it also experiences electric field acceleration from residual fields in the magnetosphere, which speeds it back up. The emitted photons travel outward. Some escape the magnetosphere entirely, becoming part of the X-ray emission we detect from Earth. Others undergo pair production, creating new electrons and positrons, continuing the cascade. Meanwhile, our original electron continues spiraling toward the magnetic pole. As it approaches the stellar surface, the magnetic field strength increases dramatically. The electron's spiral tightens, and it radiates even more intensely. Eventually, the electron either strikes the stellar surface, where it heats the polar region and contributes to the thermal X-ray emission, or it bounces back due to the increasing field strength, traveling along the field line toward the opposite pole. This back-and-forth motion can continue for some time, with the electron bouncing between the two magnetic poles, radiating all the while, until it finally loses enough energy to be captured by the surface or annihilates with a positron. Multiply this process by billions upon billions of particles throughout the magnetosphere, and you begin to see why magnetars shine so brightly in X-rays. But the magnetosphere isn't just a static structure with particles flowing along field lines. It's dynamic, constantly evolving, and subject to instabilities. One key phenomenon is called magnetic reconnection in the magnetosphere. Remember that magnetic reconnection is the sudden rearrangement of magnetic field lines, releasing stored energy. We discussed how this happens in the stellar crust during giant flares, but it also happens in the magnetosphere. The magnetosphere's field lines are constantly being twisted by the star's rotation and by motions in the stellar interior. This twisting stores energy in the magnetic field configuration. Eventually, the configuration becomes unstable. Field lines of opposite polarity are brought together. They reconnect suddenly, snapping into a new lower energy configuration. The energy difference is released as particle acceleration and radiation. This magnetospheric reconnection can happen on much shorter timescales than crustal starquakes, milliseconds to seconds rather than fractions of a second. It might be responsible for the short, frequent bursts of X-rays and gamma rays that magnetars produce between their rare giant flares. Another important phenomenon is the propagation of Alfvén waves in the magnetosphere. Alfvén waves are oscillations in the magnetic field that travel along field lines. They're named after Hannes Alfvén, the physicist who first described them. When a starquake or flare disturbs the stellar surface, it launches Alfvén waves into the magnetosphere. These waves propagate outward along magnetic field lines at speeds determined by the field strength and plasma density. As the waves travel, they can accelerate particles, heat the plasma, and modify the structure of the magnetosphere. They might also be responsible for some of the quasi-periodic oscillations observed in magnetar X-ray emission, regular pulsations with periods of milliseconds to seconds that appear during and after bursts. Understanding these oscillations is like doing seismology on the magnetosphere. By analyzing the frequencies and damping times of oscillations, astronomers can infer properties of the magnetospheric plasma and magnetic field. The magnetosphere also interacts with the stellar surface in ways that affect the crust. Remember that the crust is under enormous magnetic stress. The magnetosphere provides a boundary condition, the magnetic field must match smoothly between the solid crust and the plasma-filled magnetosphere. If the magnetosphere undergoes a sudden change, say due to reconnection, this can exert a torque on the crust, potentially triggering a starquake. Conversely, a starquake in the crust can send disturbances into the magnetosphere, triggering bursts and flares. This coupling between the interior, the crust, and the magnetosphere makes magnetars a complex, interconnected system. You can't understand one component in isolation. The entire structure, from the superconducting core to the crustal lattice to the pair plasma magnetosphere, functions as a unified whole. Let's also consider the role of the magnetosphere in the magnetars spin-down. As we've discussed, magnetars spin down rapidly due to magnetic braking. But what exactly is applying the braking torque? It's the magnetosphere. Specifically, it's the particle wind flowing outward from the magnetosphere, carrying away angular momentum. As particles flow along open field lines into space, they remain magnetically connected to the star. Because the magnetic field is rotating with the star, these outflowing particles are forced to co-rotate out to the light cylinder radius. Beyond that, they break free, but they carry away angular momentum in the process. This is similar to how a garden sprinkler loses angular momentum when water sprays from the rotating arms. The outflowing water carries angular momentum away, causing the sprinkler to slow down. For a magnetar, the outflowing particles play the role of the water. The rate of angular momentum loss, and thus the spin-down rate, depends on the magnetic field strength, the particle wind rate, and the field geometry. By observing the spin-down rate, astronomers can infer these properties and test models of the magnetosphere. There's also observational evidence for magnetospheric processes in the form of spectral features in the X-ray emission. Magnetos show absorption and emission lines in their X-ray spectra. Specific energies, where photons are absorbed or emitted by atoms in the magnetosphere or stellar atmosphere. These lines are often highly unusual, shifted and broadened by the intense magnetic field. By modeling these features, astronomers can determine the field strength, the plasma composition, and the temperature at different locations in the magnetosphere. One particularly interesting feature observed in some magnetars is the presence of absorption lines from ionized iron at unexpectedly low energies. This suggests that iron atoms in the magnetosphere are in highly ionized states, but are also significantly affected by the magnetic field, which shifts their energy levels. Analyzing these spectral features is like doing spectroscopy on an environment billions of times more extreme than anything achievable in a laboratory. It's a window into exotic atomic physics in action. The magnetosphere also plays a role in the magnetar's long-term evolution. As the magnetic field decays over thousands of years, the magnetosphere shrinks, the light cylinder moves inward. The pair cascade becomes less vigorous. The X-ray luminosity decreases. Eventually, the magnetosphere might become too weak to sustain a dense pair plasma. At this point, the magnetar might transition to a more pulsar-like state, where radio emission becomes dominant and X-ray emission fades. Some astronomers have suggested that certain isolated pulsars with peculiar properties, unusually long spin periods, high magnetic fields, or erratic timing behavior might be old, faded magnetars in this transitional state. The magnetosphere is also where we might expect to see effects from general relativity. The strong gravity near the neutron star surface curves spacetime significantly. This curvature affects how photons travel through the magnetosphere, how particles orbit, and how the magnetic field itself is structured. Some theoretical models have explored how general relativistic effects modify magnetospheric structure. For instance, the closer to the star you get, the more spacetime curvature bends the paths of particles and photons. This can affect the location and strength of acceleration regions, potentially influencing the observed emission. Observations haven't yet been precise enough to clearly detect these relativistic magnetospheric effects, but future missions with higher sensitivity might be able to. Finally, let's consider a speculative but intriguing idea. Could magnetospheres be particle accelerators rivaling or exceeding anything humans have built? The Large Hadron Collider accelerates protons to energies of about 7 trillion electron volts, 7 TeV. This is achieved using superconducting magnets and radio frequency cavities in a ring 27 kilometers in circumference. Magnetospheres, with their extreme magnetic fields and strong electric field components, could potentially accelerate particles to comparable or even higher energies over much shorter distances. Some models suggest particles in magnetospheres could reach energies of tens to hundreds of TeV. If so, magnetars could be natural particle accelerators, producing ultra-high energy cosmic rays. These cosmic rays, particles traveling through space at nearly the speed of light, are detected on Earth, but their sources are uncertain. Magnetars are one candidate. However, there's a complication. For particles to reach us from a magnetar, they must escape the magnetosphere and travel through the galaxy without losing energy. This is challenging, especially for electrons and positrons, which radiate energy rapidly when deflected by galactic magnetic fields. Heavy nuclei, protons, iron nuclei, can travel farther without losing energy. If magnetars accelerate such nuclei, they could contribute to the cosmic ray flux, especially at the highest energies. This connection between magnetars and cosmic rays is still speculative, but it's an active area of research. Future observations with cosmic ray detectors and gamma-ray telescopes might reveal whether magnetars are significant cosmic ray sources. The magnetosphere, then, is far more than just an empty region around the star. It's a complex, dynamic structure, a laboratory where plasma physics, magnetic reconnection, particle acceleration, and relativistic effects all play out under the most extreme conditions nature provides. Understanding the magnetosphere is crucial to understanding magnetars themselves. It's where the star's energy is converted into the light we observe, where particles are accelerated to enormous energies, and where the magnetic field interacts with the cosmos beyond the stellar surface. Now, with our understanding of magnetospheres complete, let's turn to another crucial aspect of magnetar physics: how these objects evolve over time and what their life cycle tells us about the universe. The story of magnetar discovery is a tale of mysterious signals, incorrect theories, and gradual revelation. It's a reminder that the universe often surprises us, presenting phenomena we didn't predict and couldn't have imagined. The story begins in the late 1970s with the detection of strange bursts of gamma rays coming from space. These bursts were unlike anything astronomers had seen before. Gamma rays are the highest energy form of light, photons with energies millions of times greater than visible light. They're produced by the most energetic processes in the universe: nuclear explosions, particle collisions at near light speed, and matter falling into black holes. Starting in 1979, satellites designed to detect gamma-ray bursts, originally built to monitor for nuclear weapons testing from space, began recording peculiar events. These weren't the typical gamma-ray bursts that come from distant galaxies. These were something different. The sources were located in our own galaxy, the Milky Way. The bursts would arrive suddenly, unpredictably, releasing enormous amounts of energy in seconds or less, and they would repeat from the same locations, something true gamma-ray bursts never did. Astronomers called them soft gamma repeaters, or SGRs. Soft because the gamma rays were at somewhat lower energies than typical bursts, still incredibly energetic, but not as extreme as cosmological gamma-ray bursts. Repeaters, because they would flare up multiple times from the same source. At first, no one knew what they were. The leading theories involved binary star systems, accreting black holes, or some exotic stellar process. But none of the models quite fit the observations. Then, on March 5, 1979, something extraordinary happened. A massive burst of gamma rays swept through the solar system, detected by satellites orbiting Earth and by interplanetary probes. The burst was so intense, it triggered sensors designed to detect nuclear weapons, setting off alarms at military installations. The burst lasted only a fraction of a second, but in that brief moment, it released more energy than the sun produces in 1,000 years. The gamma rays ionized Earth's upper atmosphere, causing measurable disruptions. Soviet Venera spacecraft en route to Venus recorded the event. Satellites in Earth orbit were temporarily blinded. Astronomers traced the source to a location in the Large Magellanic Cloud, a small galaxy about 160,000 light-years from Earth. The source was designated SGR 0526-66, and it had just produced the most energetic burst of electromagnetic radiation ever recorded. This event galvanized the astronomical community. Clearly, something extreme was happening. But what could produce such power? Through the 1980s and early 1990s, several more soft gamma repeaters were discovered. Each would occasionally burst, releasing high-energy radiation detectable across the galaxy. Between bursts, many were also found to emit steady X-rays, pulsing as they rotated. This pulsation was key. It indicated these objects were rotating, with a rotation period measurable in seconds. For SGR 0526-66, the period was about 8 seconds. For others, it ranged from 5 to 12 seconds. These rotation periods were puzzling. They were slower than typical young pulsars, which rotate tens to hundreds of times per second. But they were faster than the oldest, slowest pulsars known, and crucially, the rotation was slowing down. The periods were gradually lengthening over time. By measuring how quickly the rotation slowed, astronomers could estimate the age of these objects. They appeared to be young, only a few thousand to tens of thousands of years old. This matched their suspected locations in or near supernova remnants, the expanding shells of debris from exploded stars. But young neutron stars should be rotating rapidly, not slowly, and they shouldn't be producing such enormous bursts of high-energy radiation. Something didn't add up. The breakthrough came in 1992, when astronomers Robert Duncan and Christopher Thompson proposed a radical idea. These objects were neutron stars with extraordinarily strong magnetic fields so powerful they dominated the star's behavior. They called them magnetars. Duncan and Thompson's calculations showed that if a neutron star had a magnetic field of about 10 circumflex, 15 Gauss, 1,000 times stronger than typical neutron stars, it would behave exactly as the soft gamma repeaters behaved. The strong magnetic field would act as a powerful brake on the star's rotation, rapidly slowing it down. This explained why magnetars rotated slowly, despite being young. The energy stored in such an intense magnetic field, if suddenly released through reconnection or a starquake, could power the observed bursts. This explained the gamma-ray eruptions, and the gradual decay of the magnetic field through the crust would heat the star's surface, explaining the persistent X-ray emission observed between bursts. The magnetar model fit the observations beautifully, but it was a radical proposal. No one had predicted such strong magnetic fields could exist on neutron stars, and there was no direct observational confirmation. That confirmation came gradually through the 1990s and 2000 as observations improved. X-ray telescopes in space, particularly NASA's Chandra X-ray Observatory and ESA's XMM Newton, were able to study magnetars in detail between their dramatic eruptions. They found that magnetars had spectra, the distribution of energy across different X-ray wavelengths that matched theoretical predictions for magnetic field-dominated neutron stars. The surfaces were hotter than they should be for neutron stars of their age, consistent with magnetic field decay heating the crust. The X-ray pulsations showed evidence of atoms being stretched by intense magnetic fields, creating unique spectral features. And crucially, astronomers began measuring the actual magnetic field strength through an indirect but reliable method, the spin-down rate. As a magnetar rotates, its misaligned magnetic field acts like a rotating magnet, generating electromagnetic radiation that carries away energy. This magnetic braking causes the rotation to slow down gradually. By measuring how quickly the rotation period lengthens, you can calculate the magnetic field strength needed to produce that braking. For the known soft gamma repeaters, these calculations gave field strengths of 10 circumflex 14 to 10 circumflex 15 Gauss, exactly in the magnetar range predicted by Duncan and Thompson. The case was becoming overwhelming. But the ultimate proof came from observing the magnetar's most spectacular phenomena, giant flares. After the 1979 giant flare from SGR 0526-66, two more were observed from other magnetars. one in August 1998 from SGR 1900+14, and one in December 2004 from SGR 1806-20. The 2004 flare from SGR 1806-20 was the most powerful ever recorded. Despite occurring 50,000 light-years away, it briefly became the brightest object ever seen in the sky in gamma rays, outshining everything except the sun. The flare had a distinctive structure. An initial spike of intense gamma rays lasted about 1/10 of a second, releasing about 10 circumflex 46 ergs of energy. This was followed by a pulsating tail, oscillations in the X-ray brightness with multiple frequencies that lasted several minutes. These oscillations were seismic vibrations of the neutron star crust, excited by the giant flare. By analyzing the frequencies, astronomers could study the star's structure, much like seismologists use earthquake waves to study Earth's interior. The observations matched magnetar theory perfectly. The energy, the spectrum, the pulsations, everything fit the model of a massive magnetic reconnection event on the surface of a neutron star with a quadrillion Gauss magnetic field. By the early 2000s, the magnetar model was established. But there was a surprise still to come. Astronomers had also been studying another class of mysterious objects, anomalous X-ray pulsars, or AXPs. These were neutron stars that emitted X-rays and rotated with periods of several seconds, but they didn't show the dramatic bursts of soft gamma repeaters. For years, AXPs were thought to be a different type of object, perhaps neutron stars accreting material from a companion star or powered by some other process. But as observations improved, it became clear that AXPs and soft gamma repeaters had many similarities. They rotated at similar rates, they slowed down at similar rates, they had similar X-ray spectra and temperatures, and occasionally, AXPs would produce bursts of gamma rays, just like soft gamma repeaters, just less frequently and with lower intensity. By the mid-2000s, astronomers realized that AXPs and soft gamma repeaters were the same type of object, just observed at different activity levels. They were all magnetars, neutron stars with ultra-strong magnetic fields. The only difference was that some magnetars were more active, producing frequent bursts and occasional giant flares, while others were quieter, showing only steady X-ray emission and rare, weak bursts. This unified picture meant there were more magnetars than previously thought. As of today, astronomers have confirmed about 30 magnetars in our galaxy and the nearby Magellanic Clouds, with possibly many more awaiting discovery. Observing magnetars requires space-based telescopes because the X-rays and gamma rays they emit are absorbed by Earth's atmosphere. Missions like NASA's SWIFT, Fermi and NewStar, along with ESA's XMM Newton and Integral, continuously monitor the sky for magnetar bursts and study them in detail. These observations have revealed fascinating details. Magnetars show variability on all timescales. Sudden bursts lasting milliseconds, flares lasting minutes, and gradual changes in their X-ray emission over months and years. Some magnetars have been observed to undergo outbursts, periods lasting months, where their X-ray brightness increases dramatically and they produce frequent bursts. Then they settle back into a quieter state. The triggers for these outbursts are still being studied. Radio observations have added another layer. While magnetars were initially thought to be radio quiet, unlike typical pulsars, which emit strong radio waves, several have been found to produce transient radio emission, especially during and after outbursts. This has blurred the line between magnetars and ordinary pulsars, suggesting that the magnetic field strength exists on a continuum, with magnetars at the extreme end, but not completely separate from other neutron stars. Optical observations have also been made of a few magnetars, detecting faint visible light from their hot surfaces. This is challenging because magnetars are so distant and so compact, but it's been accomplished for the closest ones. Perhaps most remarkably, astronomers have recently begun using the unique optical properties of magnetized vacuum to study magnetar magnetic fields directly. By observing how light from a magnetar is polarized, meaning its electromagnetic waves oscillate in a particular orientation, we can detect vacuum birefringence caused by the extreme magnetic field. In 2016, the European Space Agency's XMM Newton telescope detected this effect for the first time, confirming that space around a magnetar is indeed polarized by quantum vacuum effects predicted decades earlier, but never observed until magnetars provided a natural laboratory strong enough to produce them. These observations have turned magnetars from theoretical curiosities into real laboratories for extreme physics, places where we can test theories of quantum electrodynamics, nuclear matter, and general relativity under conditions impossible to reproduce on Earth. But magnetars aren't just interesting for physics. They also tell us about stellar evolution, supernova explosions, and the life cycles of massive stars. They're pieces of a larger cosmic story. Let's explore how magnetars fit into the life cycle of stars and what they reveal about stellar death and birth. Every magnetar begins as a massive star. Not just any star, but one born with at least 8 to 10 times the mass of our Sun, and likely much more massive still. Perhaps 20, 30, or even 50 solar masses. These massive stars live fast and die young. While our Sun will shine for about 10 billion years, a star 20 times more massive might last only 10 million years. It burns its nuclear fuel at a prodigious rate, fusing hydrogen into helium, then helium into carbon and oxygen, then onward through the periodic table, creating ever heavier elements. This fusion happens in shells, like layers of an onion. The core fuses the heaviest elements, while outer layers continue fusing lighter ones. Eventually, the core becomes primarily iron element, 26, with 26 protons. And here, fusion stops. Iron is the most stable nucleus. Fusing iron into heavier elements doesn't release energy. It requires energy. There's no longer any outward pressure from fusion to balance gravity. The core is doomed. In less than a second, the iron core, about 1.5 times the mass of the Sun and roughly the size of Earth, collapses under its own gravity. It shrinks from thousands of kilometers across to about 20 kilometers. The density increases by a factor of 1 billion. This collapse is called core bounce, and it releases an enormous amount of gravitational energy, about 10 circumflex 53 ergs, which is more energy than the Sun will produce in its entire 10 billion year lifetime, released in less than a second. Most of this energy, about 99%, is carried away by neutrinos, ghostly particles that barely interact with matter. They stream outward from the collapsing core at nearly light speed, passing through the outer layers of the star as if they weren't there. But 1%, still an enormous amount, goes into heating the infalling outer layers and driving a shockwave outward. This shockwave tears through the star, heating material to billions of degrees and triggering a spectacular supernova explosion. The outer layers are blasted into space at speeds of thousands of kilometers per second. They create an expanding shell of gas that will eventually spread across light years, enriching the interstellar medium with heavy elements created in the star and the explosion. This is where the elements that make up planets and life come from. They're forged in massive stars and scattered by supernovae. But at the center, the collapsed core remains. In most cases, this becomes a neutron star. In the most massive cases, it collapses further into a black hole. Now here's the key question for our story. What determines whether this newborn neutron star becomes an ordinary neutron star or a magnetar? The answer likely lies in the details of the collapse and the original star's properties. Specifically, its rotation speed and magnetic field. Massive stars, like all stars, rotate as gas clouds collapse to form stars. Conservation of angular momentum means they spin faster, just like an ice skater pulling in their arms. Most massive stars rotate at speeds of tens to hundreds of kilometers per second at their surface. Some massive stars, however, rotate even faster. If a massive star rotates very rapidly, this has several important consequences. First, rapid rotation affects the star's structure. It makes the star somewhat flattened at the poles and bulging at the equator. It can drive mixing between different layers, affecting how nuclear fusion proceeds. Second, rapid rotation affects the magnetic field. Stars have magnetic fields generated by dynamo processes. Churning motions in conducting fluids, combined with rotation, A rapidly rotating star with strong convective motions can generate a powerful magnetic field. Third, when the core collapses, conservation of angular momentum means the rotation speed increases dramatically. A core rotating once per day when it's Earth-sized might rotate once per second when it's 20 kilometers across. The rotation speed scales inversely with the square of the radius. And fourth, the collapse amplifies the magnetic field. Magnetic flux is conserved during collapse. Roughly speaking, the magnetic field lines get compressed along with the matter. As the core shrinks, the magnetic field strength increases. For a typical massive star, the core might have a magnetic field of about 100 to 1000 Gauss before collapse. After compression to neutron star dimensions, this becomes 10 circumflex, 11 to 10 circumflex 12 Gauss, the field strength of an ordinary neutron star. But if the original star had an unusually strong magnetic field, perhaps 10,000 Gauss, and was rotating rapidly, the collapse could produce a much stronger field on the neutron star, 10 circumflex, 14 to 10 circumflex, 15 Gauss, magnetar territory. Additionally, there's likely a dynamo process operating during and immediately after the collapse. The incredibly hot, churning, rapidly rotating matter in the newborn neutron star can amplify magnetic fields dramatically through magneto-hydrodynamic processes. Some theoretical models suggest that if conditions are just right, very rapid rotation, strong initial magnetic field, vigorous convection, a runaway dynamo can occur during the first few seconds after core bounce. The magnetic field grows exponentially, reaching quadrillion Gauss strengths before the neutron star settles into stability. This is still an area of active research. The exact conditions required to produce a magnetar versus an ordinary neutron star aren't fully understood, but it's clear that only a subset of massive stars, perhaps 10 to 20%, produce magnetars when they explode. There's another intriguing possibility. Some astronomers have suggested that binary stars, pairs of stars orbiting each other, might be particularly likely to produce magnetars. In a close binary system, two massive stars orbit each other, sometimes close enough that they interact. One star might pull material from its companion, or the two might even merge during their evolution. If two stellar cores merge during the supernova process, this could create the extremely rapid rotation and strong magnetic field needed for a magnetar. The merging cores would have enormous angular momentum and complex magnetic field geometries, potentially triggering the runaway dynamo. This might explain why some magnetars are found in clusters or associations of young stars, where binary interactions are common. Whatever the formation mechanism, the result is a newborn magnetar, a neutron star with a quadrillion Gauss magnetic field, rotating several times per second, with a surface temperature of millions of degrees. This newborn magnetar is extraordinarily energetic. Its magnetic field is stressed and twisted from the formation process. Its crust is still settling from the sudden collapse, and it's spinning rapidly, with enormous rotational energy. Over the next few thousand years, the magnetar evolves rapidly. The magnetic field exerts a powerful braking torque, slowing the rotation. The spin period increases from milliseconds or fractions of a second to several seconds. This spin down converts rotational energy into magnetic energy and heat. The magnetic field itself evolves. Currents in the superconducting core decay slowly, causing the magnetic field to weaken over time, a process called ohmic decay. But this decay is slow, taking tens of thousands of years. Meanwhile, the stressed magnetic field produces starquakes and bursts. The crust fractures repeatedly as it adjusts to the magnetic stresses. Each fracture produces a burst of X-rays and gamma rays. Occasionally, the magnetic field becomes unstable and undergoes a large-scale reconnection event, a giant flare. These flares might happen once every few decades or centuries during the magnetar's active phase. The surface cools gradually as the star radiates away its thermal energy. But magnetic field decay heats the crust, keeping the surface hotter than an ordinary neutron star of the same age. After about 10,000 years, the magnetar enters middle age. Its rotation has slowed to periods of 10 seconds or more. The magnetic field has decayed somewhat, though it's still much stronger than ordinary neutron stars. Starquakes and bursts become less frequent. Eventually, after perhaps 100,000 years, the magnetar becomes quiescent. The magnetic field has decayed to levels comparable to ordinary neutron stars, still enormous by terrestrial standards, but no longer extreme enough to dominate the star's behavior. At this point, the magnetar might become indistinguishable from older pulsars. It might emit radio waves as a typical pulsar, or it might be largely silent, a cooling neutron star gradually fading into darkness. This life cycle, from violent birth through active youth to quiet middle age, explains the population of magnetars we observe. Most of the magnetars we've discovered are young, still in their active phase. They're bright in X-rays, they produce bursts, and occasionally they flare dramatically. There are likely many more magnetars in the galaxy that have aged past their active phase and are no longer easily detectable. They're still there, still neutron stars with remnant strong magnetic fields, but no longer producing the dramatic phenomena that originally revealed their existence. Understanding magnetar birth and evolution connects them to the broader story of stellar life cycles. They're not separate objects, unrelated to other stars. They're part of the continuum of stellar death, representing the endpoint for a particular subset of massive stars. And they're important cosmic players. Let's explore their impact on their surroundings and their significance in the broader universe. Magnetars are not eternal. Like all objects in the universe, they're born, they evolve, and they eventually fade. Understanding this life cycle, how magnetars change over thousands to millions of years, gives us insight into their nature and helps us interpret the diverse population we observe. Let's trace a magnetar's life from violent birth to quiet old age. Phase 1. The first seconds. Violent birth. A magnetar's life begins in the most violent moments imaginable, the core collapse of a massive star. We've discussed this process, but let's focus now on what happens in those first crucial seconds after the collapse. At the moment of core bounce, when the collapsing iron core rebounds, the proto-neutron star is incredibly hot, with temperatures exceeding 1 trillion degrees Kelvin. At these temperatures, neutrinos are produced in enormous quantities through nuclear reactions and electron capture. The proto-neutron star is initially larger than its final size, perhaps 50 kilometers in radius rather than 20. Over the next 10 to 20 seconds, it cools and contracts as neutrinos carry away energy. This neutrino cooling phase is called the Kelvin-Helmholtz phase. During these first seconds, if the proto-neutron star is rotating rapidly, perhaps once every few milliseconds, and if convective currents are vigorous, the dynamo mechanism can amplify magnetic fields explosively. What began as a field of perhaps 10 circumflex 12 Gauss from flux compression can grow to 10 circumflex 15 Gauss through magnetohydrodynamic instabilities. This runaway dynamo operates only briefly. Within 10 seconds or so, the convection settles down, the neutrino luminosity decreases, and the magnetic field stabilizes. But by then, the magnetar's defining characteristic, its ultra-strong magnetic field, has been established. The newborn magnetar is now about 20 kilometers in diameter, spinning perhaps once per second, with a surface temperature of several million degrees and a magnetic field of 1 Gauss. It's ready to begin its active life, phase 2, infancy. The first 1,000 years. During its first 1,000 years, the magnetar is at its most violent and energetic. This is the phase when most of the magnetars we observe are found, because they're brightest and most active. The rotation period is short, perhaps 1 to 5 seconds initially. The magnetic field exerts an enormous braking torque, slowing the rotation steadily. The spin-down power, the rate at which rotational energy is converted to other forms, is enormous, perhaps 10 circumflex 36 ergs per second. For comparison, the sun's luminosity is 4 × 10 circumflex 33 ergs per second. The newborn magnetar is outputting energy at a rate hundreds of times greater than the sun, just from its rotational energy alone. Where does this energy go? Some goes into electromagnetic radiation, X-rays and gamma rays. Some goes into heating the crust through magnetic field decay. Some goes into particle winds streaming from the magnetosphere. And some gets stored in the twisted magnetic field, waiting to be released in bursts and flares. During this phase, starquakes are frequent, perhaps one every few decades, or even more often. Each starquake releases a burst of high-energy radiation detectable across the galaxy. Giant flares might occur every few centuries, rare even for an individual magnetar, but somewhere in the galaxy, one happens every few decades. The surface temperature during this phase remains high, sustained not just by residual heat from formation, but by magnetic field decay. As currents in the superconducting core dissipate slowly, they heat the interior, and this heat diffuses outward, keeping the surface at millions of degrees. The magnetar is also shrouded in a supernova remnant during this phase. The debris from the exploded star is expanding outward at thousands of kilometers per second, but it hasn't yet dispersed. The magnetar sits at the center of this glowing shell, its own emission competing with the supernova's fading light. Astronomically, this is when magnetars are easiest to detect. They're bright, they're active, they produce dramatic bursts that catch astronomers' attention. Many of the known magnetars are in this youthful phase. Phase 3. Adolescence. Thousands to tens of thousands of years. After about 1,000 years, the magnetar enters adolescence. The rotation has slowed to periods of 5 to 10 seconds or longer. The spin-down power has decreased significantly, perhaps to 10 circumflex 34 to 10 circumflex 35 ergs per second, still enormous but diminished from the peak. The magnetic field begins to show signs of decay. The surface field strength might decrease from 10 circumflex 15 Gauss to a few times 10 circumflex 14 Gauss. This is still vastly stronger than ordinary neutron stars, but the trend is downward. Starquakes become less frequent, perhaps one every few centuries now. Giant flares are rarer still. The magnetar spends most of its time in a relatively quiescent state, emitting steady X-rays from its hot surface and magnetosphere, with only occasional bursts. The surface temperature remains elevated, but it's cooling gradually as the magnetic field decay slows. The magnetosphere is still dense with pure plasma, but less so than in the early years. By now, the supernova remnant has expanded and thinned. It might be light years across, a faint shell barely visible in X-rays and radio waves. The magnetar is more isolated, no longer embedded in dense debris. Observationally, magnetars in this phase are still detectable, but less dramatically so. They might go years or decades without producing a burst strong enough to attract attention. Some might be classified as anomalous X-ray pulsars rather than soft gamma repeaters, appearing more subdued. This is a longer phase than infancy, lasting perhaps 10 to 20,000 years. During this time, the magnetar is slowly transforming from a violent, eruptive object to a more stable, quieter neutron star. Phase 4. Middle age, tens to hundreds of thousands of years. By the time a magnetar reaches 100,000 years old, it has changed considerably. The rotation period has lengthened to tens of seconds or even minutes. The magnetic field has decayed to perhaps 10 circumflex, 13 to 10 circumflex 14 Gauss, still strong, but approaching the realm of ordinary high-field pulsars. The spin-down power is now relatively modest, perhaps 10 circumflex, 32 to 10 circumflex 33 ergs per second. This is comparable to ordinary young pulsars. The magnetar-specific phenomena, the giant flares, the frequent bursts, have essentially ceased. Starquakes are extremely rare, perhaps once every few millennia. The surface has cooled significantly. Magnetic field decay still provides some heating, but it's much reduced. The surface temperature might be a few 100,000 degrees, hot by terrestrial standards, but cool for a neutron star. The magnetosphere is no longer filled with dense pure plasma. The particle cascade is much weaker. The X-ray emission has faded substantially. The magnetar might now be emitting primarily in soft X-rays and UV, rather than the hard X-rays and gamma rays of its youth. Observationally, magnetars in this phase are difficult to detect unless they're relatively nearby. They're faint in X-rays, they don't produce dramatic bursts, and they might be hard to distinguish from old, ordinary pulsars. In fact, it's likely that many middle-aged magnetars go unrecognized. They're still out there in the galaxy, but without distinctive features to mark them as special, they blend into the general population of old neutron stars. Some might emit radio waves, becoming radio pulsars with unusually long periods and relatively high magnetic fields. Others might be radio quiet, detectable only as faint X-ray sources, if at all. This phase is the longest in the magnetar's active life, lasting perhaps hundreds of thousands of years. But even it must eventually end. Phase 5, old age, millions of years. After 1,000,000 years or more, the magnetar has effectively retired. The magnetic field has decayed to 10 circumflex, 12 Gauss or less, comparable to ordinary pulsars. The rotation period is measured in minutes or even hours. The spin-down power is negligible. The surface has cooled to perhaps 100,000 degrees or less. At these temperatures, thermal emission is in the far UV or soft X-rays, and it's extremely faint. Without a telescope specifically looking for it, the magnetar would be invisible. The magnetosphere is tenuous. There's little pair production, minimal particle acceleration, and essentially no high-energy emission. If the magnetar emits radio waves, and not all old neutron stars do, it might be detectable as an ordinary, if slowly rotating pulsar. Magnetar-specific phenomena are long gone. No bursts, no flares, no starquakes. The object has completed its transformation from an extreme magnetar to a relatively ordinary old neutron star. Observationally, magnetars in this phase are nearly impossible to distinguish from other old neutron stars. They're faint, they're quiet, and they lack distinctive features. Only detailed measurements, perhaps revealing a remnant strong magnetic field or peculiar spectral properties, might hint at their magnetar past. There are likely thousands of these aged magnetars in our galaxy, quietly cooling and spinning down, their violent youths long forgotten. We've probably detected some without recognizing them as former magnetars. Phase 6, the final silence, beyond 10 million years. Eventually, on timescales of tens of millions of years, even the faint emission from old age ceases. The surface cools below 50,000 degrees. Thermal emission shifts into the optical and infrared, and it's so faint that detection is nearly impossible. The rotation has slowed to periods of many hours or even days. The magnetic field has decayed to perhaps 10 circumflex, 10 to 10 circumflex, 11 Gauss, still stronger than anything on Earth, but weak by neutron star standards. At this point, the magnetar has become a black widow, a dark neutron star, cooling and spinning down in the depths of space, essentially invisible to our instruments. It will continue cooling for billions of years, eventually reaching thermal equilibrium with a cosmic microwave background at about 3 degrees Kelvin. It will spin ever more slowly, the magnetic field decaying asymptotically towards zero, but never quite reaching it. In the far future, trillions of years from now, long after the last stars have burned out, the magnetar will still exist, a cold, dark sphere of neutron-degenerate matter, a relic of a universe that once burned brightly. But that's so far in the future, it's essentially meaningless. For practical purposes, after 10 million years, the magnetar's story is over. Understanding the population. This life cycle explains the population of magnetars we observe. Most of the detected magnetars are young, in the infancy or adolescence phases. They're the ones producing dramatic bursts and flares that catch our attention. A smaller number are in middle age, still detectable but quieter, and the vast majority, the old and ancient magnetars, are essentially invisible to us with current technology. By studying magnetars at different ages, astronomers can piece together this life cycle. We can see how the magnetic field decays, how the rotation slows, how the emission evolves. We can test theoretical models of magnetic field evolution and crustal physics against observations. This also tells us about the production rate. If there are about 30 observable magnetars in the Milky Way, and each one is detectable for about 20,000 years, then new magnetars must be created every few hundred years on average. Given that massive star supernovae occur about once per century in our galaxy, this suggests roughly 10 to 20% of massive star core collapses produce magnetars. The rest produce ordinary neutron stars or black holes. This percentage is uncertain and depends on assumptions about detection efficiency and magnetar lifetimes. But it gives us a rough sense of how special magnetars are. Not extremely rare, but definitely a minority among neutron stars. Reactivation and surprises. There's an interesting twist to this life cycle. Some magnetars seem to reactivate after long periods of quiescence. An old magnetar, thought to be retired, suddenly produces a burst or enters an outburst state. This suggests that the evolution isn't entirely smooth and predictable. Perhaps an old, decayed magnetic field can occasionally undergo a sudden rearrangement, releasing stored energy and temporarily reviving magnetar-like activity. Or perhaps there are external triggers, interactions with the interstellar medium, accretion of material, or even impacts from asteroids or comets left over from the original star system. These reactivations are rare but observed. They remind us that even our best models are simplified versions of complex reality. Nature always has surprises. The cycle's broader implications. Understanding the magnetar life cycle also informs our understanding of stellar evolution broadly. Magnetars are one endpoint of massive star evolution. By studying them, we learn about the full range of outcomes when massive stars die. This connects to questions about star formation, galactic chemical evolution, and the history of star formation across cosmic time. In distant galaxies, when star formation was more vigorous, were magnetars more common? Are there ancient magnetars from the early universe, now cooled and invisible? We can also connect magnetar evolution to the history of our own galaxy. Some of the oldest magnetars might have formed in the early Milky Way, billions of years ago, when the galaxy was young and metal-poor. These ancient magnetars are now dark and undetectable, but they're still out there, silent witnesses to the galaxy's youth. The life cycle of magnetars is a microcosm of cosmic evolution, from violent birth through active maturity to quiet old age and eventual darkness. It mirrors the life cycles of stars, galaxies, and perhaps even the universe itself. And it reminds us that everything changes. Nothing in the cosmos is eternal. Even the most extreme objects, magnetars with their incomprehensible magnetic fields and explosive violence, are transient, fading slowly into the darkness as time passes. But while they shine, they're magnificent. And by studying them across all phases of their lives, we're learning not just about magnetars, but about the nature of time, change, and evolution in the cosmos. Magnetars don't exist in isolation. They're embedded in a cosmic context, surrounded by the remnants of their birth supernova, immersed in the interstellar medium, sometimes orbiting companion stars. Their extreme physics affects their environment in ways both subtle and dramatic. Let's start with the immediate aftermath of the supernova that creates a magnetar. When a massive star explodes, it ejects most of its mass into space. This expanding shell of gas, the supernova remnant, contains several solar masses of material traveling outward at thousands of kilometers per second. It's hot, dense, and turbulent, glowing brightly in X-rays and visible light. At the center of this expanding debris sits the newborn magnetar, spinning rapidly and pulsing with high-energy radiation. The magnetar's powerful magnetic field and intense radiation affect the surrounding supernova remnant. The magnetar emits a wind of high-energy particles, electrons and positrons, accelerated to near light speed by the rotating magnetic field. This wind inflates a bubble inside the supernova remnant called a pulsar wind nebula. Even though magnetars spin down quickly and don't have the sustained energy output of faster rotating pulsars, they still produce these nebula during their first few thousand years. Some magnetar candidates have been identified precisely because they sit at the center of young supernova remnants with distinctive properties. One example is RCW 103, a supernova remnant about 10,000 light-years away. At its center is a neutron star called 1E1613485055, which showed puzzling behavior for years. It emitted X-rays with a rotation period of 67 hours, far too slow for a young pulsar, but too fast for an old neutron star accreting from a companion. In 2016, this object produced a bright X-ray outburst, and detailed observations revealed it was actually a magnetar. The unusually slow rotation was likely due to fallback material from the supernova accumulating around the star, providing extra braking beyond magnetic spin-down. This discovery highlighted how magnetars can have diverse interactions with their birth environments. Some might be slowed by fallback material, others might have had their rotation influenced by binary interactions. Each magnetar tells a slightly different story. Beyond the supernova remnant, magnetars interact with the broader interstellar medium, the thin gas that fills the space between stars. As a magnetar moves through the galaxy, and all stars move, orbiting the galactic center at hundreds of kilometers per second, it plows through this interstellar gas. The magnetar's magnetic field and particle wind create a bow shock, similar to the wake behind a boat. The shape and structure of this bow shock can reveal information about the magnetar's motion, its magnetic field geometry, and the properties of the surrounding gas. Some magnetars have been observed to have extended X-ray emission around them, likely from these interactions. Magnetars also emit neutrinos, ghostly particles produced by nuclear processes in their incredibly hot interiors. These neutrinos stream outward, carrying away energy and cooling the star. While neutrinos are nearly impossible to detect individually due to their weak interactions with matter, the cumulative effect of neutrino cooling significantly affects the magnetar's temperature evolution. Future neutrino observatories might be able to detect the neutrino glow from nearby magnetars, providing a unique window into their interior physics, a way to see inside the neutron star itself. But perhaps the most dramatic way magnetars affect their environment is through giant flares. When a magnetar produces a giant flare, it doesn't just light up the star itself, it impacts everything nearby. The 2004 giant flare from SGR 1806-20 provides a powerful example. This magnetar is about 50,000 light-years away, on the opposite side of the galaxy from Earth. Yet when it flared, the gamma rays that reached Earth were intense enough to ionize our upper atmosphere. Satellites orbiting Earth were temporarily blinded by the radiation. Radio communications were disrupted. If a spacecraft had been exposed directly to the burst without shielding, its electronics could have been damaged or destroyed. Now imagine being much closer, at a distance of 10 light-years, which is close by galactic standards. There are dozens of stars within 10 light-years of Earth. A similar giant flare would deliver radiation doses comparable to being near a nuclear explosion. It would strip away portions of planetary atmospheres, damage surface environments, and potentially cause mass extinctions. Fortunately, no magnetars are known to be that close to us. The nearest confirmed magnetar is about 9,000 light-years away. At that distance, even a giant flare is merely an interesting astronomical event, not a threat. But in the distant past, if a magnetar had existed close to early Earth, its flares could have influenced the development of life, perhaps sterilizing the surface and forcing life to persist only in oceans or underground, or perhaps providing bursts of mutation causing radiation that accelerated evolution. This is speculative, but it highlights how magnetars, despite being small objects, can have significant cosmic impacts through their extreme energy releases. Magnetars also play a role in galactic chemical evolution. As part of the population of neutron stars produced by massive star supernovae, they represent endpoints in the cycle of matter through stars. The supernovae that create magnetars scatter heavy elements into space: carbon, oxygen, silicon, iron, and everything else up through the periodic table. These elements eventually become incorporated into new generations of stars and planets. The atoms in your body were created in stars and scattered by supernovae, possibly including events that produced magnetars. Furthermore, there's a tantalizing connection between magnetars and another cosmic mystery: fast radio bursts, or FRBs. FRBs are brief, intense pulses of radio waves coming from distant galaxies. They last only milliseconds, but release as much energy in that brief flash as the sun produces in days. Their origin was unknown for years, with dozens of theories proposed. In April 2020, astronomers detected an FRB coming from within our own galaxy, specifically from a known magnetar called SGR 1935 plus 2154. This was the first time an FRB had been detected from a galactic source, and the first time one was definitively associated with a magnetar. The discovery strongly suggested that at least some FRBs are produced by magnetars in distant galaxies. The exact mechanism is still debated. It might involve magnetic reconnection, starquakes, or interactions with the magnetar's magnetosphere, but the connection seems clear. This has profound implications. If magnetars produce FRBs, then the thousands of FRBs detected across the universe trace the magnetar population in distant galaxies. By studying FRBs, we can learn about magnetars billions of light-years away, far too distant to detect through their X-rays. This also means FRBs could be used as probes of the intergalactic medium, the thin gas between galaxies. As radio waves travel through space, they interact slightly with free electrons, causing dispersion. Different frequencies arrive at different times. By measuring this dispersion for FRBs at different distances, we can map the distribution of matter between galaxies. So magnetars, through their connection to FRBs, have become tools for cosmology, helping us understand the large-scale structure of the universe. There's another exotic possibility involving magnetars. Could they be responsible for mysterious gravitational wave signals? Gravitational waves are ripples in space-time produced by accelerating masses, typically detected from merging black holes or neutron stars. But there are theoretical predictions for other sources, including deformed neutron stars. If a neutron star has a permanent deformation, a mountain or a bulge on its surface, its rotation creates a time-varying gravitational field that produces continuous gravitational waves. For an ordinary neutron star, this deformation would need to be only millimeters high, but sustained against the star's enormous gravity. Magnetars, with their intense magnetic fields creating stresses in the crust, could potentially sustain larger deformations. Some models suggest magnetar crusts could support mountains kilometers high, especially if the magnetic field creates an asymmetric stress pattern. If so, magnetars could be sources of continuous gravitational waves. These waves would be much weaker than the dramatic chirps from merging compact objects, but they could be detected with long observation times by detectors like LIGO and Virgo. Searches for continuous gravitational waves from known magnetars are ongoing. So far, none have been detected, but upper limits from these searches constrain the possible deformations and tell us about neutron star crust properties. As gravitational wave detectors become more sensitive, magnetars remain intriguing targets. A detection would provide unprecedented information about neutron star interiors and magnetic field effects on stellar structure. Magnetars also intersect with another exotic topic, gamma-ray bursts. Traditional long-duration gamma-ray bursts, the most energetic explosions in the universe after the Big Bang, are produced by the collapse of massive stars into black holes. But a subset of bursts, particularly some with very long durations or peculiar properties, might be produced by magnetars. If a magnetar forms with extremely rapid rotation, spinning hundreds of times per second, and with an ultra-strong magnetic field, it could power a gamma-ray burst through its spin-down energy. As the magnetic field breaks the rotation, the energy could be channeled into jets of particles moving at near light speed, producing the burst. This magnetar model for gamma-ray bursts is an alternative to the black hole model, and it might explain some observed bursts with unusual characteristics, particularly those that show evidence for continued energy injection after the initial explosion, as would be expected if a magnetar were gradually spinning down. Some astronomers have even suggested that certain supernovae, called superluminous supernovae, which are far brighter than ordinary supernovae, might be powered by magnetars. If a magnetar forms and spins down rapidly in the center of an expanding supernova remnant, its energy could heat and illuminate the debris, making it shine exceptionally brightly for weeks or months. These connections between magnetars and other astrophysical phenomena show how the study of extreme objects often reveals unexpected linkages. The universe is interconnected, and magnetars sit at several intersection points in that cosmic web. But magnetars aren't just interesting for what they tell us about astrophysics. They're also natural laboratories for fundamental physics, places where we can test theories under conditions impossible to achieve on Earth. Let's explore what magnetars teach us about the basic laws of nature. Magnetars occupy a unique place in the universe, not just as astronomical objects, but as natural experiments in fundamental physics. Their extreme conditions allow us to test theories of matter, energy, and forces in regimes far beyond anything achievable in human-made laboratories. Let's start with quantum electrodynamics, the quantum theory of light and electromagnetism. QED, as physicists call it, is one of the most precisely tested theories in science. Its predictions match experiments to extraordinary precision, sometimes agreeing to 10 decimal places. But most tests of QED involve relatively weak fields and low energies. Magnetars push QED into unexplored territory. In the quantum vacuum, what we think of as empty space, particle-antiparticle pairs constantly appear and disappear. An electron and a positron pop into existence for a fraction of a second, then annihilate back into energy. This happens everywhere, all the time, as a consequence of quantum uncertainty. Normally, these virtual particles have no observable effect because they exist for such a brief time. But in a strong magnetic field, the story changes. A magnetic field affects charged particles, including virtual electrons and positrons. It aligns them, polarizes them, and changes their behavior. At magnetar field strengths, these effects become large enough to observe. One prediction is vacuum birefringence. The magnetic field makes space optically birefringent, like a crystal. Light traveling through this magnetized vacuum has different speeds depending on its polarization. This was pure theory for decades, but in 2016, astronomers using the XMM Newton X-ray telescope observed X-rays from a magnetar called RxJ 1856, 3754, and detected exactly this effect. The light was polarized in a way that could only be explained by vacuum birefringence in the intense magnetic field. This was the first direct observation of quantum vacuum effects in nature, confirming predictions made by quantum electrodynamics in strong fields. Magnetars had provided a laboratory that human technology couldn't replicate. Another exotic QED effect in magnetars is photon splitting. In the extreme magnetic field, a single high-energy photon can spontaneously split into two lower-energy photons. This sounds like it violates energy conservation, but it doesn't. It's a quantum process where the magnetic field provides the environment for the split to occur. Photon splitting affects how radiation propagates through the magnetar's magnetosphere. It changes the spectrum of emitted light in subtle but detectable ways. By comparing observations to theoretical models, including photon splitting, astronomers can test these exotic QED predictions. Magnetars also probe nuclear physics in extreme conditions. The surface of a magnetar is likely covered by a thin atmosphere, perhaps only centimeters thick, made of iron atoms or possibly exotic particles. In the intense magnetic field, iron atoms are stretched into elongated shapes. Their energy levels, the quantum states electrons can occupy, are completely rearranged. This affects how they absorb and emit light, creating unique spectral features. Astronomers have observed absorption features in magnetar X-ray spectra that match theoretical predictions for iron in extreme magnetic fields. These observations confirm our understanding of atomic physics in conditions billions of times more extreme than anything on Earth. Deeper inside the magnetar, in the crust, nuclear physics becomes even more exotic. The crust is made of neutron-rich nuclei, isotopes with far more neutrons than protons, unlike any stable atom on Earth. In a strong magnetic field, even neutrons, which have no electric charge, feel effects. They develop an induced magnetic moment, and the intense field aligns them. This affects the properties of neutron-rich matter in ways we're still working to understand. The equation of state. The relationship between pressure, density, and temperature for nuclear matter is modified by magnetic fields at magnetar strength. This affects the star's structure, its radius, its maximum mass, and how it responds to stress. By studying starquakes, giant flares, and the pulsations they excite, astronomers can probe the neutron star interior. The frequencies of oscillations depend on the crust thickness, its rigidity, and the properties of matter beneath it. These observations constrain nuclear physics models in extreme conditions. One particularly interesting question is whether magnetars have quark matter cores. At the extreme densities in neutron star centers, several times the density of atomic nuclei, protons and neutrons might break down into their constituent quarks, forming a quark-gluon plasma, similar to what existed microseconds after the Big Bang. Whether this happens depends on the equation of state, which is uncertain. But if magnetar cores contain quark matter, this would affect their oscillation frequencies, their cooling rates, and possibly their magnetic field evolution. Future observations might be able to detect signatures of quark matter in magnetar behavior. Magnetars also allow tests of general relativity, Einstein's theory of gravity. While general relativity has been tested extensively in the solar system and with binary pulsars, magnetars offer new tests in strong field regimes. A magnetar's intense gravity creates significant space-time curvature. Light from the surface is bent as it escapes, and clocks run slower near the surface due to gravitational time dilation. These effects influence what we observe. For example, the shape of X-ray pulses from a magnetar depends on relativistic beaming and light bending. As a hot spot on the rotating surface sweeps into and out of view, the pulse shape is modified by general relativity. By modeling these pulse shapes precisely, astronomers can test whether general relativity correctly describes space-time near neutron stars. Additionally, if magnetars produce continuous gravitational waves from deformations, detecting those waves would test general relativity's predictions for how mass quadruples generate space-time ripples. There's also a connection to gamma-ray bursts and relativistic jets. If magnetars power some gamma-ray bursts by channeling their spin-down energy into jets, this involves complex physics of magnetic fields, plasma, and relativity. Understanding how magnetar energy gets converted into relativistic outflows tests our understanding of magnetohydrodynamics in extreme regimes. Beyond specific physics theories, magnetars also inform our understanding of magnetic fields in general, how they're generated, how they evolve, and what limits exist on their strength. The dynamo mechanism that generates planetary and stellar magnetic fields is reasonably well understood for moderate field strengths. But at magnetar extremes, new effects become important. The magnetic field's own energy density affects the dynamics. Quantum effects modify conductivity. Relativistic effects become significant. Magnetars are laboratories for studying dynamo theory in these extreme limits. Understanding how a newborn neutron star amplifies its magnetic field to magnetar strength informs dynamo theory generally, with applications to other contexts, from planets to galaxies. There's also the question of field decay. Magnetar magnetic fields decrease over time as currents dissipate, but exactly how fast this happens depends on the conductivity of neutron star matter, which involves exotic physics we don't fully understand. By observing magnetars at different ages and measuring their field strengths, astronomers can constrain models of magnetic field decay in superconducting, superfluid, neutron-rich matter. Again, a regime with no terrestrial analog. Magnetars even touch on astrobiology in an indirect but fascinating way. Life on Earth depends on a stable environment, moderate temperatures, liquid water, a protective atmosphere, and shielding from harmful radiation. Earth's magnetic field plays a role by deflecting charged particles from the solar wind. But how important are magnetic fields for habitability? Could planets orbiting magnetars, or planets that had experienced nearby magnetar flares, still develop life? These questions are mostly academic. Magnetars are far too rare and short-lived for planets to form around them after they become magnetars. But the extreme example highlights the role of magnetic fields in planetary habitability. More relevantly, Understanding extreme magnetic environments helps us think about exotic habitats elsewhere. If microorganisms can withstand radiation and extreme environments on Earth, could similar life survive near neutron stars? Probably not near magnetars specifically, but the study of extremes helps define what life requires. Finally, magnetars connect to cosmology in subtle ways. The supernova explosions that produce magnetars contribute to the chemical evolution of galaxies. The energy they release affects the interstellar medium. Their fast radio bursts, if magnetars do produce FRBs, serve as probes of the universe's large-scale structure. And in the very early universe, shortly after the Big Bang, conditions were extreme in different ways, but with some analogies to neutron star interiors. Understanding matter under extreme density and temperature helps cosmologists model the first moments of the universe. Magnetars, then, are more than curiosities. They're windows into fundamental physics, natural laboratories where extreme conditions occur, allowing tests of theories that would otherwise remain purely speculative. And they inspire new questions. If nature can produce magnetic fields this strong, could even stronger fields exist? Are there limits? And what other extremes might the universe contain that we haven't yet imagined? Let's explore the remaining mysteries and unanswered questions about magnetars. Magnetars don't exist in isolation within the zoo of extreme astrophysical objects. They share the universe with black holes, quasars, gamma-ray bursts, pulsars, and other phenomena that push physics to its limits. Comparing magnetars to these other objects reveals both their uniqueness and their place in the broader cosmic context. Let's explore how magnetars relate to other extreme objects and what these relationships tell us about the universe. The closest relatives to magnetars are ordinary pulsars, rotating neutron stars that emit beams of radio waves. In fact, the boundary between magnetars and high magnetic field pulsars is somewhat fuzzy. Ordinary pulsars have magnetic fields of about 10 circumflex, 11 to 10 circumflex, 13 Gauss. Magnetars have fields of 10 circumflex, 14 to 10 circumflex, 15 Gauss. But the distribution is continuous. There's no sharp dividing line, just a range where objects transition from pulsar-like to magnetar-like behavior. The key difference is that magnetars' fields are strong enough to dominate their energy output and evolution. For an ordinary pulsar, the rotational energy is the primary energy source. The pulsar shines because it's spinning down, converting rotational energy into electromagnetic radiation through the rotating magnetic field. For a magnetar, the magnetic field itself is an energy source. As the field decays and rearranges, it releases energy that heats the surface and powers bursts. The rotation is still important. It provides magnetic braking, but the field's stored energy is equally or more significant. This difference manifests in several ways. Magnetars are typically hotter than ordinary pulsars of the same age because magnetic field decay provides additional heating. Magnetars show more variability, bursts and flares that ordinary pulsars don't exhibit. And magnetars spin down faster because their stronger magnetic fields provide more braking. Interestingly, some pulsars show magnetar-like behavior occasionally. They might produce high-energy bursts or show X-ray emission consistent with strong magnetic fields. These objects blur the boundary, suggesting that magnetic field strength exists on a continuum rather than falling into distinct categories. This tells us that neutron stars are more diverse than simple classification schemes suggest. The universe doesn't divide objects neatly into boxes. Instead, there's a spectrum, with magnetars at one extreme. Black holes are another endpoint of massive star evolution. While stars 8 to 20 times more massive than the Sun produce neutron stars, including magnetars, stars above about 20 to 25 solar masses produce black holes when they die. The boundary isn't sharp, it depends on the star's composition, rotation, and explosion mechanism. But broadly, magnetars and stellar mass black holes represent two possible fates for massive stars. Both are extreme in different ways. Black holes compress matter to infinite density in classical general relativity, while magnetars compress it to near nuclear density. Black holes warp space-time so severely that nothing can escape from inside the event horizon, while magnetars warp space-time significantly, but not enough to trap light. Both produce powerful emission through accretion when matter falls onto them, but the mechanisms differ. For black holes, matter forms an accretion disk that heats up through friction, emitting X-rays and sometimes producing jets. For magnetars, accretion is less common, but when it occurs, the strong magnetic field funnels material onto the magnetic poles, creating hotspots and pulsed emission. Interestingly, there's a hypothetical connection between magnetars and black holes in the context of gamma-ray bursts. Some models suggest that when a massive star collapses, there's a brief period, seconds to minutes, where a proto-neutron star exists before collapsing into a black hole. If this proto-neutron star has magnetar strength fields and rotates rapidly, it could power a gamma-ray burst during its brief existence. Then, as it collapses into a black hole, the burst ends. This magnetar black hole transition model is speculative but intriguing. There's also a curious parallel in the no-hair theorem for black holes. This theorem states that black holes are characterized by only three properties: mass, charge, and angular momentum. All other information about what fell into the black hole is lost. Magnetars, in contrast, retain complexity. Their magnetic fields have structure, dipoles, quadrupoles, higher-order components. Their crusts have mountains and fractures. They have thermal gradients and internal layers. They're complicated objects, yet both magnetars and black holes represent extreme simplicity in a sense. Magnetars are the simplest structure you can have at nuclear densities while remaining stable against collapse. Black holes are the simplest structure allowed by general relativity. They're each the endpoint of a process that destroys complexity, leaving only the most fundamental properties. Quasars are supermassive black holes at the centers of galaxies, actively accreting matter and shining with luminosities that can exceed entire galaxies. They're among the most luminous objects in the universe. At first glance, magnetars and quasars seem unrelated. Quasars are millions to billions of times more massive, billions of times more luminous, and exist in galactic centers rather than in isolation or supernova remnants. But there's a fascinating connection through magnetic fields. Quasars are thought to have magnetic fields threading their accretion disks. These fields, while much weaker than magnetar fields in absolute strength, perhaps 10 circumflex 3 to 10 circumflex 5 Gauss, play a crucial role in quasar physics. They generate turbulence in the disk, transport angular momentum, and potentially launch the powerful jets observed in many quasars. In both magnetars and quasars, magnetic fields store enormous energy. For magnetars, this energy is released in starquakes and flares. For quasars, it's released through jets and disk emission. Both involve magnetic reconnection, the sudden rearrangement of field lines, releasing energy. In magnetars, reconnection happens on kilometer scales in fractions of a second. In quasars, it happens on astronomical unit scales, distances comparable to Earth's orbit, over hours to days. But the fundamental physics is similar. Some researchers have explored whether magnetar-like processes might occur near supermassive black holes. Could the twisted magnetic fields in the inner regions of quasar accretion disks undergo magnetar-like eruptions, producing flares and variability? This is speculative, but it highlights how magnetic field physics studied in magnetars might have applications across vastly different scales and contexts. When two neutron stars orbit each other, their orbits decay due to gravitational wave emission. Eventually, after millions or billions of years, they spiral into each other and merge, an event of unimaginable violence. These neutron star mergers produce gravitational waves detected by LIGO and Virgo, gamma-ray bursts, and kilonovae optical and infrared transients powered by radioactive decay of heavy elements synthesized in the merger. The product of a neutron star merger is typically a rapidly rotating, highly magnetized object, either a short-lived hypermassive neutron star that quickly collapses into a black hole, or a long-lived supermassive neutron star stabilized by rapid rotation. Could some of these merger remnants be magnetars, Simulations suggest that the magnetic fields in merging neutron stars can be amplified dramatically by the violent churning and shearing during coalescence. Post-merger, the remnant might have a field of 10 circumflex 15 to 10 circumflex 16 Gauss at or beyond typical magnetar strengths. If the remnant survives collapse, which depends on the total mass and equation of state, it would be a rapidly rotating magnetar, spinning perhaps hundreds of times per second initially, then spinning down on timescales of minutes to years. This merger-formed magnetar could power extended emission following the merger, X-rays and gamma rays lasting minutes to days. There's some observational evidence for this in the aftermath of neutron star merger GW1708-17, where X-ray emission was detected months to years after the event, possibly from a magnetar remnant. If merger remnants do form magnetars, this would be a distinct formation channel separate from core collapse supernovae. These merger-born magnetars might have different properties, faster initial spins, different magnetic field geometries, or unique evolutionary paths. Understanding this connection helps us interpret gravitational wave observations and predict what we'll see with future detections. Let's zoom out to the largest scales. The universe itself has magnetic fields, intergalactic magnetic fields with strengths of about 10 circumflex 16 to 10 circumflex 14 Gauss, and galactic magnetic fields with strengths of about 10 circumflex 6 Gauss. These cosmic magnetic fields, while extraordinarily weak by terrestrial or stellar standards, have important effects. They influence the propagation of cosmic rays, affect star formation, and contribute to the dynamics of galaxies and galaxy clusters. Where do cosmic magnetic fields come from? This is an unsolved problem in astrophysics. Some might be primordial, dating from the early universe. Others are generated by dynamos in stars and galaxies, but the exact processes are uncertain. Magnetars might contribute to cosmic magnetic fields in subtle ways. When magnetars produce giant flares, they release magnetized plasma into the interstellar medium. This plasma carries magnetic field with it, potentially amplifying or seeding larger-scale fields. Additionally, the particle winds from magnetars, electrons, positrons, and ions streaming into space are magnetized. These winds could inject magnetic flux into supernova remnants and the surrounding ISM, contributing to the galactic magnetic field over time. The contribution from magnetars is likely small compared to other sources like supernova shocks and galactic dynamos. But on very long timescales, over the life of a galaxy, the cumulative effect of thousands of magnetars might be significant. This connects the smallest magnetic structures, magnetar crusts, to the largest, galactic and intergalactic fields, showing how magnetic phenomena span every scale in the universe. Beyond the well-known categories, there are speculative or exotic stellar objects that might relate to magnetars. One hypothetical object is a quark star, a neutron star where the density is so high that neutrons break down into quarks, forming a quark-gluon plasma. If quark stars exist, they could have even stronger magnetic fields than magnetars, potentially reaching 10 circumflex 16 to 10 circumflex 17 Gauss. These quark magnetars would show similar phenomena to neutron magnetars, bursts, flares, X-ray emission, but with even more extreme energies. Observationally, distinguishing them from neutron magnetars is challenging, but subtle differences in oscillation frequencies or cooling rates might provide clues. Another exotic possibility is a strange star, a star made of strange quark matter, which some theories suggest might be more stable than normal nuclear matter. Strange stars could also have extremely strong magnetic fields, and they might be hiding in the magnetar population, indistinguishable from ordinary magnetars with current observations. These ideas are speculative, but they remind us that our understanding of ultra-dense matter is incomplete. Magnetars might not all be standard neutron stars. Some could harbor exotic cores or be composed of matter in states we've only theorized. Finally, let's consider magnetars in unusual contexts. Most magnetars are isolated, born in supernovae. They drift through the galaxy alone, but some might exist in extreme environments that modify their behavior. A magnetar near a supermassive black hole at a galactic center would experience intense tidal forces and might accrete from dense gas clouds in the region. This could trigger unusual outbursts or alter its magnetic field evolution. A magnetar in a dense star cluster might occasionally pass close to other stars, leading to interactions, captures, or even collisions. Such events would be rare but spectacular. And in the early universe, conditions were different. Stars were metal-poor, possibly more massive on average, and formed in different environments. Early universe magnetars might have had different properties, and their descendants might still exist today as ancient, cold neutron stars. These scenarios are mostly speculative, but they expand our thinking about where and how magnetars might exist beyond the standard picture. By comparing magnetars to other extreme objects, pulsars, black holes, quasars, merger remnants, we see both their uniqueness and their connections. Magnetars are special, but they're also part of a continuum of extreme astrophysics. They share physics with objects across vastly different scales, and they help us understand the universe's capacity for creating extremes. Despite decades of observation and theoretical work, magnetars still hold many mysteries. Every answer raises new questions, and the universe continues to surprise us with phenomena we didn't predict. One fundamental question remains: how common are magnetars really? We've detected about 30 magnetars in the Milky Way and nearby galaxies. But the galaxy contains hundreds of millions of stars, and massive stars that could produce magnetars are born at a rate of about 1 per century. If 10 to 20% of massive star supernovae produce magnetars, and these magnetars remain active and detectable for about 10,000 years, there should be hundreds or thousands of active magnetars in our galaxy right now. Why haven't we found more? Part of the answer is observational bias. Magnetars are small, distant, and emit primarily in X-rays and gamma rays, wavelengths that require space telescopes. Many parts of the galaxy are obscured by dust clouds that block our view, and magnetars aren't always active. They go through quiet periods where they're difficult to detect. So there are likely many undiscovered magnetars lurking in the galaxy, either in remote locations, behind dust clouds, or in inactive states. But there's also a deeper question. Do all magnetars follow the same evolutionary path? Or are there subtypes with different behaviors? Recent observations suggest diversity among magnetars. Some rotate fast, others slow. Some produce frequent bursts, others are quiet. Some show strong persistent X-ray emission, others are faint between bursts. Some emit radio waves, others don't. This diversity hints at variation in their formation conditions, magnetic field geometries, or evolutionary histories. Understanding what determines a magnetar's properties requires connecting observations to theoretical models of their birth and evolution. Another mystery involves the mechanism of giant flares. We've observed 3 giant flares in detail, and each showed similar features: an initial spike followed by pulsating X-ray emission. But we still don't fully understand the trigger. What causes the magnetic field to suddenly undergo catastrophic reconnection? Is it the buildup of stress from gradual field twisting? A starquake that disturbs the field? An instability in the magnetosphere? And why do giant flares happen so rarely? Some magnetars have been observed for decades without producing one. Others have produced multiple. What determines whether a magnetar will flare, and when? Related to this is the question of outbursts, periods lasting months when a magnetar becomes much more active, producing frequent bursts and increased X-ray emission. Several magnetars have been observed to undergo outbursts, then return to quiescence. What triggers an outburst? Models suggest it might involve a sudden event, like a small starquake or magnetic instability that cascades into sustained activity. But the detailed mechanism remains unclear. There's also the puzzle of magnetar timing behavior. Magnetars spin down as their magnetic fields break their rotation, but the spin down isn't perfectly smooth. Magnetars show timing irregularities, glitches where the rotation suddenly speeds up slightly, and timing noise where the rotation rate wanders unpredictably. Glitches are seen in other pulsars, and are thought to involve sudden unpinning of superfluid vortices in the neutron star interior. But magnetar glitches might have an additional magnetic component, where starquakes or field rearrangements cause sudden changes in the moment of inertia or magnetic braking torque. Understanding these timing anomalies provides clues to the neutron star interior, how the superfluid core couples to the solid crust, and how the magnetic field threads through different layers. Then there's the connection to fast radio bursts, the detection of an FRB from the galactic magnetar SGR 1935 plus 2154 strongly suggests magnetars produce at least some FRBs. But not all FRBs can come from magnetars. Some repeat at rates far too high, and some come from galaxies with low star formation where magnetars should be rare. Are there multiple types of FRBs with different origins? Do magnetars produce only a subset? And what exactly is the emission mechanism? Models range from magnetic reconnection in the magnetosphere to interactions with the magnetar's environment to exotic processes we haven't thought of yet. Resolving this will require more detections of FRBs from galactic magnetars, which are rare events, and detailed multi-wavelength observations to compare FRB properties with magnetar behavior. Another open question involves the role of fallback material. In some supernovae, material blown outward in the explosion falls back onto the neutron star, forming a disk of debris. This fallback can affect the magnetar's evolution, providing additional braking, perhaps triggering outbursts, and potentially feeding material onto the surface. We have evidence for fallback disks around some magnetars, but how common they are and how they affect magnetar behavior is still being explored. There's also the question of binary companions. Most massive stars are in binary systems. When one star explodes as a supernova, what happens to the companion? If the companion survives, the magnetar might be in a binary system, orbiting another star, perhaps interacting with it. A few magnetars are suspected to have companions, but confirmations are difficult because the magnetar's brightness overwhelms the companion in X-rays. Binary magnetars could have unique behaviors, outbursts triggered by tidal interactions, accretion from the companion star, or orbital evolution driven by magnetic braking. They're a largely unexplored frontier. Then there's the deep interior. We've discussed neutron star structure in general terms, but the exact state of matter at densities several times that of atomic nuclei is uncertain. Is it pure neutron matter? A neutron-proton-electron mixture? Quark matter? Hyperons? Kaon condensates? Different models predict different equations of state, which affect the neutron star's radius, moment of inertia, and oscillation frequencies. By comparing theoretical predictions to observations, especially detailed timing and oscillation data from magnetars, we can constrain the equation of state. This is one of the most important unsolved problems in physics. What are the properties of ultra-dense matter? Magnetars provide crucial data for answering this question. There's also an exotic possibility. Could some neutron stars be even stranger than magnetars? Could there be objects with stronger magnetic fields, or with properties we haven't imagined? Some theorists have speculated about electro-weak stars, where magnetic fields are so strong they affect the weak nuclear force, or objects with toroidal magnetic field geometries hidden inside, potentially even stronger than magnetar surface fields. These are speculative, but the history of neutron star astronomy is one of repeated surprises. We discovered pulsars when we didn't expect them. We found magnetars when we thought we understood neutron stars. What else might be out there? Another mystery involves the galactic center, the region around the supermassive black hole at the heart of our galaxy. This region is crowded with stars, including many massive ones. It should be a prolific magnetar factory, yet we've detected relatively few magnetars there. Why? Is it because the environment is so crowded and variable that magnetars are hard to pick out? Or is there something about star formation near the galactic center that suppresses magnetar production? Recent observations with Chandra and NuStar have identified several magnetar candidates near the galactic center, but many questions remain. There's also the long-term fate of magnetars. After their active phase, they presumably become ordinary pulsars or quiet neutron stars. But do they retain any distinctive signatures? Could old inactive magnetars be responsible for some unexplained phenomena? For example, there's a class of faint X-ray sources called central compact objects found at the centers of some supernova remnants. They don't show pulsations or strong magnetic braking, yet they're hotter than expected. Some be old magnetars that have spun down and faded, but still retain internal heat from magnetic field decay. This connects to another question. How long do strong magnetic fields last? Theoretical models predict decay timescales of tens to hundreds of thousands of years, but observational confirmation is difficult because we can't watch a single magnetar evolve over such long times. By studying magnetars of different ages and comparing their field strengths and spin periods, astronomers can infer decay rates, but the sample size is still small, and individual magnetars might evolve differently. Finally, there's the question of formation mechanism. We've discussed the likely scenario: rapid rotation, strong initial fields, dynamo amplification, but the details remain murky. Numerical simulations of core collapse and magnetar formation are incredibly challenging. They must model extreme physics, nuclear densities, strong magnetic fields, relativistic flows, neutrino transport in 3 dimensions over timescales from milliseconds to seconds. Even the most powerful supercomputers struggle with this. Recent simulations have made progress, showing that rapid rotation and strong magnetic fields can indeed produce magnetar-strength fields during collapse. But we're still working toward realistic, self-consistent models that can predict what fraction of massive stars become magnetars and what determines their properties. These open questions ensure that magnetar research will remain active for decades. Each new observation brings surprises, and each advance in theory opens new possibilities. But perhaps the most profound mystery is philosophical. Why does nature allow such extreme objects to exist? What does the existence of magnetars tell us about the universe's capacity for extremes? Let's reflect on what magnetars mean in the broader cosmic context. We've explored what we know about magnetars, their physics, their observations, their mysteries. But science is a journey, not a destination. The magnetar story is far from complete. New telescopes, new detectors, and new theoretical tools will reveal much more in the coming years and decades. Let's look ahead to the future of magnetar research. What questions will address, what technologies will help us, and what discoveries might await. Next generation X-ray telescopes. X-ray astronomy is crucial for magnetar science because magnetars emit primarily in X-rays. Current missions like Chandra, XMM Newton, and NewStar have been invaluable, but they're aging. New missions will provide dramatic improvements. NASA's upcoming mission, called AXIS, Advanced X-ray Imaging Satellite, planned for the 2030s, will have unprecedented sensitivity and spatial resolution in X-rays. It will be able to detect faint magnetar emission from distant sources, study magnetar magnetospheres in fine detail, and resolve spectral features that current telescopes can't. ESA's Athena, Advanced Telescope for High-Energy Astrophysics, also planned for the 2030s, will have excellent spectroscopy capabilities. It will measure X-ray spectra with energy resolutions 10 times better than current missions, allowing detailed studies of atomic lines, continuum emission, and variability. With these capabilities, astronomers will be able to detect and study magnetars in distant galaxies, not just the Milky Way and Magellanic Clouds, map the temperature distribution across magnetar surfaces, testing models of heat transport in the crust, measure the magnetic field strength directly from cyclotron absorption features in spectra, study the evolution of magnetar emission over time with continuous monitoring, detect and characterize old, faint magnetars that are currently below detection thresholds. These missions will dramatically expand the known magnetar population and allow statistical studies that are currently impossible with small samples. Gravitational wave astronomy. Gravitational wave detectors like LIGO and Virgo have opened an entirely new window on the universe. While most detections so far have been merging black holes or neutron stars, magnetars might also be gravitational wave sources. If magnetars have permanent deformations, mountains or bulges on their surfaces, their rotation produces continuous gravitational waves. These waves are much weaker than merger signals, but they could be detected with long observation times. Current detectors haven't yet detected continuous waves from magnetars, but future upgrades will improve sensitivity significantly. LIGO and Virgo are planning upgrades to A+ configurations in the mid-2020s, and the next-generation Einstein telescope and Cosmic Explorer, planned for the 2030s and 2040s, will be 10 times more sensitive. These improvements will allow detection of continuous waves from nearby magnetars if their mountains are higher than a few millimeters. Measurements of magnetar moments of inertia and interior structure from wave signals. Detection of gravitational waves from starquakes and giant flares, providing real-time diagnostics of these events. Studies of gravitational wave emission from neutron star merger remnants, which might be magnetars. Combining gravitational wave observations with X-ray and gamma-ray data will provide complementary information. Gravitational waves probe the interior structure, while electromagnetic waves probe the surface and magnetosphere. Multi-messenger astronomy. The future of magnetar research is multi-messenger, combining information from electromagnetic waves, gravitational waves, neutrinos, and possibly even cosmic rays. Neutrino detectors like IceCube in Antarctica and the future Hyperkamiokande in Japan might be able to detect neutrinos from nearby magnetar flares. When a magnetar erupts, the heated crust produces neutrinos through nuclear reactions. These neutrinos escape directly, carrying information about the interior. Detecting neutrinos from a magnetar flare would be challenging. The flux is low, and magnetars are distant. But if a giant flare occurred within about 1,000 light-years, it might be detectable. Combining neutrino, X-ray, and gravitational wave observations of a single magnetar event would provide unprecedented insight into the physics involved, how energy is released, how it propagates through the crust, and how it escapes into space. Fast radio burst studies. The connection between magnetars and fast radio bursts is one of the most exciting recent discoveries. Future FRB studies will tell us much more about this connection. New radio telescope arrays are coming online, specifically designed to detect and localize FRBs. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, already operating, detects dozens of FRBs per month. The Square Kilometre Array, SKA, planned for the late 2020s, will be the largest radio telescope ever built and will detect FRBs at an unprecedented rate. With these instruments, astronomers will be able to build large statistical samples of FRBs, determining what fraction come from magnetars. Localize FRBs to specific galaxies and star-forming regions, constraining magnetar populations. Study repeating FRBs to understand what triggers repeat bursts. Use FRB dispersion measures to map the intergalactic medium. Search for gravitational wave signals coincident with FRBs from nearby magnetars. If magnetars produce most FRBs, then FRB studies become a way to study magnetars in distant galaxies, effectively extending our reach billions of light-years. Observations are only half the story. Theoretical understanding must advance in parallel. Future computational power and better physics models will allow more realistic simulations of magnetars. Current simulations of magnetar formation and evolution are limited by computational power. Simulating the core collapse of a massive star in 3 dimensions, including all relevant physics, nuclear reactions, magnetic fields, general relativity, neutrino transport, is at the edge of what's possible even with supercomputers. But computational power is increasing. Exascale computers, capable of a billion calculations per second, are coming online in the 2020s. These will allow much more detailed simulations. Future simulations will be able to model the entire collapse and bounce process self-consistently, predicting which stars produce magnetars, simulate the evolution of the magnetic field over thousands of years, testing decay models. model magnetospheric processes in full three-dimensional magnetohydrodynamics. Predict the detailed emission from magnetars, comparing directly to observations. Better models of ultra-dense matter. The equation of state will also help. This requires input from nuclear physics experiments with rare isotopes, quantum chromodynamics calculations, and observations of neutron star masses and radii. By constraining the equation of state through multiple methods, we'll better understand what's inside magnetars and how their interiors affect their observable properties. Some aspects of magnetar physics can be studied in laboratories on Earth, albeit in much weaker fields. High-powered lasers can create magnetic fields up to about 10 circumflex, 8 Gauss, millions of times weaker than magnetars, but still strong enough to probe some relevant physics. Laser facilities like the National Ignition Facility, NIF, in the US and the Laser Megajoule, LMJ, in France, can produce extreme states of matter, high temperatures, high densities, strong magnetic fields for fractions of a second. Future experiments might study atomic physics in magnetic fields up to 10 circumflex, 8 Gauss, extrapolating to magnetar strength. Investigate nuclear matter at high densities, informing equation of state models. Explore magnetic reconnection in laboratory plasmas, testing models of magnetar magnetospheres. While we can't replicate magnetar conditions fully, even partial explorations help validate theoretical models. As observations accumulate, archival data becomes increasingly valuable. Old observations might contain unrecognized magnetar signals. New analysis techniques might extract information missed in earlier analyses. Machine learning and artificial intelligence are already being applied to astrophysics. These tools can search through vast datasets, years of satellite observations, millions of X-ray images, looking for patterns that human eyes might miss. Future AI-driven searches might identify faint magnetar candidates in archival X-ray data, detect subtle periodicities or correlations in magnetar timing data, predict when magnetars might burst based on historical patterns, classify magnetars into subtypes based on multi-dimensional parameter spaces. Data mining could reveal hidden magnetars or discover new phenomena in well-studied objects. Philosophical and theoretical questions. Beyond empirical research, there are deep theoretical questions about magnetars that might be addressed through pure thought and mathematical physics. Why does nature allow magnetic fields as strong as 10 circumflex, 15 Gauss, but apparently not much stronger? Is there a fundamental limit, or just a practical one, based on how neutron stars form? Could there be even more extreme objects, hypothetical, hypermagnetars, with fields of 10 circumflex, 16 or 10 circumflex 17 Gauss? What would they look like? Would they be stable? How does quantum chromodynamics, the theory of quarks and the strong force, behave at densities several times nuclear density? Do quark stars exist, and if so, can they be magnetars? What role did magnetars play in the early universe? Were there magnetars in the first generation of stars billions of years ago? Could ancient cold magnetar remnants still exist? These questions blend astrophysics with fundamental physics and even philosophy. They push the boundaries of what we can know and imagine. Finally, magnetars have enormous potential for public engagement. They're inherently fascinating. Objects so extreme they challenge imagination, yet real and observable. Future educational efforts might include virtual reality experiences, simulating what it's like near a magnetar, citizen science projects where volunteers analyze magnetar data, interactive simulations allowing exploration of magnetar physics, public alerts when magnetars burst, similar to alerts for gravitational wave detections. By engaging the public, we not only share the wonder of these objects, but also inspire the next generation of scientists who will continue magnetar research in decades to come. By mid-century, what might we know about magnetars that we don't know today? We might have a catalogue of thousands of magnetars across the universe. From nearby examples studied in exquisite detail to distant ones visible only through their FRB's confirmed detections of gravitational waves from magnetar deformations or flares, detailed models of magnetar interiors validated by multiple observations. Understanding of the full range of magnetar behaviors and evolutionary paths perhaps even detection of exotic objects like quark magnetars or strange stars. Or we might have encountered surprises, new phenomena we didn't predict, objects that don't fit our models, mysteries that deepen rather than resolve. That's the nature of science. Every answer raises new questions. Every discovery opens new frontiers. Magnetars have already taught us much about extreme physics. In the coming decades, they'll teach us even more. The journey continues, and the universe, as always, has surprises waiting for those patient and curious enough to look. Magnetars exist at the edge of physical possibility. Their magnetic fields are about as strong as theory suggests matter can support. Their densities approach the fundamental limits of how tightly matter can be packed. Their rotation, their energy output, their violence, all push to extremes. This raises a profound question. Why does the universe allow such objects to exist? One answer is that the universe is governed by physical laws, fundamental principles like quantum mechanics, relativity, and thermodynamics, and within those laws, a vast range of phenomena is possible. Stars, planets, black holes, galaxies, each represents a solution to the equations of physics under particular conditions. Magnetars are another solution. They emerge naturally when massive stars collapse under gravity, when rotation and magnetic fields are amplified by compression, and when nature finds a stable configuration for this extreme state. In this view, magnetars aren't special or unusual. They're simply one more manifestation of the laws that govern everything. The fact that they seem extreme to us reflects our perspective as beings adapted to gentle environments, not any fundamental strangeness in the universe. Another perspective is that magnetars represent the universe exploring the possibility, space of physics. In the early universe, shortly after the Big Bang, conditions were extreme in all directions, incredibly hot, incredibly dense, filled with energy and particles in states we never see today. As the universe expanded and cooled, it settled into the calmer state we experience now. But in certain locations, the cores of stars, the interiors of black holes, the surfaces of neutron stars, some of that early extremity persists, allowing us to study physics that otherwise existed only in the first moments of creation. Magnetars are windows to those extreme regimes. By studying them, we're learning about physics that applied everywhere in the early universe, but now exists only in rare, isolated pockets. There's also a more practical perspective. The existence of magnetars reminds us how little of the universe resembles Earth. We're adapted to specific conditions. A planet orbiting a particular type of star at a particular distance, with a particular atmosphere and magnetic field and temperature. These conditions are rare. Most of the universe is cold vacuum. Most matter is in stars or interstellar gas, not planets. Most of space is shaped by gravity, magnetic fields and radiation in ways very unlike our cozy planetary surface. Magnetars drive this point home. They're objects where almost everything we take for granted doesn't apply. Atoms are distorted beyond recognition. Space itself is polarized by magnetic fields. Light behaves in strange ways. The surface is so dense that a teaspoon weighs as much as a mountain. Yet, magnetars are real. They exist. We detect them, we study them, and we're learning that even in such alien environments, physics works. The same quantum mechanics that describes atoms in your body describes atoms on a magnetar surface. The same general relativity that explains GPS satellite orbits explains space-time curvature near neutron stars. The laws of physics are universal. They apply everywhere, in every condition, no matter how extreme. This universality is one of the most profound discoveries of science. Magnetars also remind us that the universe is dynamic and violent on cosmic scales. We tend to think of space as peaceful, empty, silent, unchanging, and on human timescales, it often is. But on longer timescales, the cosmos is turbulent. Stars explode, galaxies collide, black holes merge, magnetars erupt, releasing in seconds more energy than our sun produces in millennia. These events shape the universe. They create and destroy. They forge heavy elements and scatter them across space. They trigger star formation and quench it. They produce neutrinos, gravitational waves, cosmic rays, messengers that travel across the universe, connecting distant events. We are products of this cosmic violence. The carbon in your muscles, the iron in your blood, the oxygen you breathe, all were created in stars and scattered by supernovae. Some of those supernovae produced magnetars. In a sense, we're made of stardust from events like these. This creates a connection across space and time. The atoms in your body were once in massive stars, billions of years ago. Those stars exploded, some creating magnetars. The remnants mixed with interstellar gas, forming new generations of stars and planets. Eventually, some ended up in the solar system, in Earth, in living organisms. You carry pieces of ancient cosmic violence within you. This is both humbling and wondrous. Magnetars also inspire awe in a more direct way. Their sheer extremity, fields quadrillions of times stronger than anything on Earth. Densities incomprehensibly high, energies beyond our everyday experience, forces us to expand our intuition. We evolved to navigate a world of moderate temperatures, low speeds, weak fields. Our brains are adapted to think about trees, animals, stones, objects at human scales, with human energies. But the universe doesn't care about our intuitions. It contains phenomena far outside our experience. Black holes, where time stops. Quantum fluctuations, where particles appear from nothing. Vast cosmic voids, empty for hundreds of millions of light years. And magnetars, where magnetism becomes a dominant force, reshaping reality. Grappling with these extremes stretches our minds. It reminds us that reality is stranger and richer than we might assume. And it demonstrates the power of science. Through observation, mathematics, and careful reasoning, we can understand phenomena utterly unlike anything in our direct experience. We can calculate the properties of matter at nuclear densities. We can model magnetic fields a quadrillion times stronger than any we've created. We can predict how light behaves in quantum vacuum influenced by those fields, and then observe it and find our predictions confirmed. This is science at its best, extending human understanding beyond the familiar, into realms we'll never visit but can nonetheless comprehend. And finally, magnetars remind us that there's always more to discover. 25 years ago, magnetars were theoretical speculations. Today, they're observed realities with a rich phenomenology. 25 years from now, what will we know? What new mysteries will observations have revealed? Perhaps we'll have detected gravitational waves from magnetars, probing their interiors in unprecedented ways. Perhaps we'll have confirmed the magnetar-FRB connection and used FRBs to map the universe. Perhaps we'll have observed magnetars in distant galaxies with next-generation telescopes, studying their evolution across cosmic time. Or perhaps we'll have discovered something entirely unexpected, a new type of neutron star, a new explosion mechanism, a new extreme of physics. The universe has surprised us before. It will surprise us again. And magnetars, as laboratories of extreme physics, are likely to play a role in those surprises. As we drift towards sleep, reflecting on these cosmic extremes, we can appreciate how far human understanding has reached, from questioning the lights in the night sky, to calculating the behavior of magnetic fields strong enough to reshape atoms, from wondering what stars are made of, to observing the burst of gamma rays from a starquake halfway across the galaxy. And we can look forward to what's yet to come. The story of magnetars isn't over. It's still being written, with each new observation adding another paragraph, each theoretical advance another chapter. The universe is vast, ancient, and full of wonders. Magnetars are among the most extreme, but they're part of a larger story, the story of matter and energy, stars and galaxies, the evolution of the cosmos from the Big Bang to today and beyond. Let's close with some final reflections on what magnetars mean and what they teach us about the universe we inhabit. We've journeyed through the physics of magnetars, from their violent birth in supernovae to their extreme magnetic fields, from their dramatic flares to their role as cosmic laboratories testing fundamental physics. Along the way, we've seen how these objects push physics to its limits. Magnetic fields so strong they warp atoms and polarize empty space. Densities so high that matter breaks down into exotic states. Energies so immense they can affect planetary atmospheres from halfway across the galaxy. And yet, for all their extremity, magnetars follow the same physical laws as everything else. They obey quantum mechanics, general relativity, thermodynamics. They're strange, but not inexplicable. They're extreme, but not beyond understanding. This is the lesson magnetars teach us, that the universe is comprehensible, even in its most alien corners. That human minds, through observation and reason, can grasp phenomena utterly unlike everyday experience. That the laws of nature are truly universal, applying not just on Earth, but in the most extreme environments imaginable. Magnetars also remind us of the interconnectedness of the cosmos. They're formed in supernova explosions that scatter heavy elements, enriching space with the building blocks of planets and life. Their bursts and flares produce messengers, photons, neutrinos, possibly gravitational waves that travel across the galaxy, connecting distant regions. Their extreme physics informs our understanding of matter and energy everywhere. We live in a universe shaped by extremes we'll never directly encounter. Most of space is cold vacuum. Most matter exists in stars or black holes. Most of cosmic history occurred long before Earth formed. Yet through science, we reach across those divides. We observe neutron stars thousands of light years away. We detect gravitational waves from merging black holes a billion light years distant. We study the cosmic microwave background from the edge of the observable universe, seeing light that's traveled for nearly 14 billion years. And we understand what we're seeing, not perfectly, mysteries remain, but substantially. We know what magnetars are. We know how they form, how they evolve, what powers their eruptions. We can calculate their properties and compare predictions to observations. We can use them to test theories and explore physics in conditions we can't replicate. This is humanity's great achievement, extending our understanding beyond immediate experience, learning to think about phenomena at every scale, from subatomic to cosmic, and finding unity in the laws that govern all of it. Magnetars are a gift from the universe. Objects so extreme they force us to refine our theories. So energetic they're visible across vast distances. So rich in phenomena they'll provide research questions for generations. As you drift into sleep, you can rest knowing that out there, in the depths of space, magnetars spin silently, their impossibly strong magnetic fields warping space-time and matter, occasionally erupting in flares that briefly outshine galaxies. They've been doing this for millions of years. They'll continue long after we're gone. They're part of the cosmos we inhabit, strange, extreme, magnificent reminders that the universe is far grander than we can fully imagine. And yet, through patient observation and careful thought, we can understand them. Good night.